Michael Haack from the Arnold Sommerfeld Center in Munich, talking about closed string amplitude, disc amplitudes in the pure spinor formalism. Please.
Okay, I would like to start by thanking the organizers for putting together this really interesting workshop. I really learned a lot already. And also for inviting me to present this work. So as Emilian said, it's about string scattering amplitudes in the pure spinor formalism. So there will not be any mention of string field theory in my talk. This is work in collaboration with Andreas Bischoff. It's work from last year when he was my master student, and by now he is PhD student at the Max Planck Institute here in Munich. Oops. So this is a short overview. I'll start with a very personal few slides of motivation. And then I'll give a review of the pure spinor formalism, even though I'm aware that there are a lot of people in the audience who know this much better than I do. But in the sake of maybe potential young participants, I want to give a possibly, hopefully, a self-contained introduction into the features of the pure spinor formalism, which are relevant for the scattering amplitudes. Then I'll adapt those to the closed string disk amplitudes and apply to the 2- and 1-point functions. So first of all, why disk amplitudes? Well, they are the leading quantum corrections to the sphere level in string theory, at least if you have open strings. And my personal interest, I'm interested in higher derivative corrections to the dBi action. So in particular, a term like this, which contains 4 powers of the Riemann tensor and 2 factors of the Levi-Civita tensor. All the indices, which are not shown here, are contracted with each other in some way. That won't play any role for us. And this kind of term is known to lead in 10 dimensions. It's known to lead to a correction to the 4-dimensional Einstein-Hilbert term if you compactify it on a Calabi-Yau manifold with non-vanishing Euler number. And in 2016, Green and Rodra gave some very interesting arguments using heterotic type 1 duality that seem to predict such a term. So if you're interested, I can say more about that maybe in the discussion. So the origin of such a term would be the disk and or projective plane, most likely from both. And a direct check of its presence would require a 5-point graviton amplitude, because if you expand this term around flat space, and it starts at 5th order in the graviton. That's why, because this is a rather daunting problem, I would hope that one could perform an alternative check, namely using the fact that, as I said, it leads to a correction to the Einstein-Hilbert term in 4 dimensions. So maybe one can see that one on a disk or projective plane in a setup where type 1 is compactified on a Calabi-Yau with non-vanishing Euler number. However, this raises the interesting question how a disk or projective plane amplitude of gravitons with only external polarization can actually depend on the Euler number of the internal space. So if anybody in the audience has any comments about this, I would be very interested to hear. So much about the motivation, my personal motivation in disk amplitudes. Now let me come to the announced introduction into the basics of the pure spinor formalism, which will be relevant for the closed string disk amplitudes I'm going to discuss later. So as you probably all know, one of the main advantages of the pure spinor formalism is its manifest super Poincare covariance, which means that you don't have to sum over spin structures in loop amplitudes, which are calculable in this formalism most effectively using the non-minimal formulation, which, however, I will not discuss in this talk. The equivalence to the INS formalism has been shown in many examples. I mean, all the examples have been calculated in both formalisms, they agree. But most of the examples were done with massless states. And recently there has been some interesting work also on massive states by some of the participants of this workshop also. For the application that I mentioned in my introduction, in my motivation, What I find also particularly appealing is that the pure spinor formalism can simplify calculations of amplitudes, and this has been demonstrated. I want to give you three, I think, rather impressive examples of this. Polycastro and Simpis calculated the complete quartic effective action of type 2 on a sphere level, including the fermions and Ramond-Ramond fields. And Gomez and Mafra calculated a closed string 4-point amplitude at 3-loop level, even though they only considered the leading term in an expansion for small momenta. Then there's a compact formula for an arbitrary endpoint amplitude of massless open strings on the disk by Mafra, Schlotterer, and Stieberger. Now I come to the more technical introduction into the pure spinor formalism, focusing on those aspects which will be relevant later. So here I give you the type 2b action for 10-dimensional flat spacetime. It looks relatively simple. There's a kinetic term for the embedding coordinates, 10 embedding coordinates, and these theta alpha and theta bar alpha, they are the superpartners, spacetime superpartners of the XMs. And from the position of the index, you can read off the chirality of the spinor. So both of them have the same chirality, leading to the type 2b theory. The p alphas are the canonical momenta, which in this formalism are independent degrees of freedom. Then there are the lambdas, which give the formalism its name, and these are pure spinors. So they obey this pure spinor constraint, and the W's are their canonically conjugate momenta. And these are commuting, lambda and W, and together with the fact that this pure spinor constraint implies that only 11 out of these 16 components are independent, this leads to the fact that this action actually has vanishing central charge. One last point that I want to mention, because I'll make use of it later, the theta alpha and lambda alpha, they have dimension 0, and the corresponding momenta have dimension 1. In order to write down the vortex operators in a moment, we'll also need the supersymmetric fields, composite fields of the elementary fields. So the pi m based on the partial x and the d alpha built upon the p alpha. And of course, there are also anti-holomorphic analogs of these in the type 2 theory. And the OPEs of these elementary fields appearing in the action that we'll need to perform the contractions are the standard ones. So for the X OPE, I set alpha prime to 2. And for the spinors, these are kind of the usual OPEs that you get for a BC system, like these first order systems of the spinors. One final operator that I need to introduce is the Neopotent Brst operator given by this formula. And using the pure spinor constraint and the OPE of the Ds, you can easily show that it's indeed nilpotent. And Nathan showed that the cohomology of this operator actually agrees with the one of the superstring. Now I come to the form of the massless vertex operators. Let me begin with your open string. And like in the RNS formalism, these vertex operators come in two different versions. An unintegrated version, which I denote by a superscript 0, which is linear in the pure spinor, and it's linear in this quantity A alpha, which is a superfield depending only on x and theta. There's an expansion in theta. I'll give it to you on the next slide. And these unintegrated vertex operators, they are BST closed manifestly. And then there's a different kind of vertex operators, the integrated one, which is defined by this relation, like in the RNS formalism. So it's only BST closed up to a derivative, so that it has to be integrated to be really BST invariant, hence the name. So this is much more complicated. It contains 4 superfields, but all of them kind of describe the same degrees of freedom. They're not all independent. And then there are these dimension 1 operators in front. This we introduced already, and the n is given by this expression, where gamma mn is a commutator of two ten-dimensional gamma matrices. So all these superfields, they have an expansion in theta. They describe the degrees of freedom of n equals 1 super Young-Mills in 10 dimensions, but I only give you the form here for the case where you only consider a gauge field, so a gluon if you wish, with polarization psi m. The x dependence is relatively simple. It only depends on x via such an exponential, like you are used to from the vortex operators in the RNS formalism. And then, as I said, there's a theta expansion. I only wrote down the leading terms here, and all these terms are expressed in terms of the polarization and the momentum of the gluon, and same for the others. Now let me come to the closed string, and here I'll focus on the vortex operators for fluctuations of the metric, the Kalb-Ramond field, and the dilaton. So these are the ones residing in the NS sector of the RNS string. The polarization tensor is given by the tensor product of the polarization vectors of the open string vortex operators that I just showed. And the closed string vortex operators are also given by such tensor products. A and B here can run over 0 or 1, depending on whether these factors here correspond to the form of the unintegrated or the integrated vortex operator that I showed before. And typically in calculations in the literature and the pure spinor formalism, A and B are usually chosen to be either both 0 or both 1. But we'll see that for purely closed amplitudes on a disk, you have to allow also for this mixed representation. This vortex operator contains, again, this usual exponential, which, however, I want to view as, exponential of the x, which, however, I want to view as the sum of a holomorphic and an anti-holomorphic piece. Coming from these two factors each. Now, let me review the basic steps, how you calculate tree-level correlators. So typically, what people calculated at tree level are endpoint functions of closed strings on the sphere or endpoint functions of open strings on a disk. And in these cases, the conformal killing group allows to fix a position of 3 vertex operators and integrate over the rest. And now I'll focus on the open string case because it's easier to discuss. The way to proceed is you have to integrate out the non-zero modes via Wick's theorem using these 3 Green's functions arising from the OPEs that I showed before. And at tree level, what makes the calculations much simpler than at loop level is that only the dimension 0 fields xm and theta alpha and lambda alpha have 0 modes. So that all the the dimension equals 1 fields which appeared or appear in the integrated form of the vortex operators, they have to be integrated out via Wick's theorem. So that after the Wick contractions, you end up with an expression which only contains the 0 modes of the 3 factors of lambda and the 0 modes of theta. So this F alpha beta gamma has an expansion in theta. And if you integrate over the x0 modes, you get the usual momentum delta function. So that now kind of the final, or the next step would be to perform the 0 mode integration over the 0 modes of theta and lambda. And this is done with the following 0 mode prescription based on the fact that this combination of lambdas, 3 lambdas and 5 thetas is a unique element of the Q cohomology with 3 factors of lambda. And you set this to 1 or everything which is related to this, but all the other terms which have more powers of theta or less, you set it to 0. And the rationale behind this is that we started with a product of Q closed vortex operators and every term which is Q exact shouldn't contribute in order to ensure gauge invariance. So this effectively projects out the coefficient of this lambda cubed theta 5 term in this expression here. And then finally, you still have to integrate over the positions of the integrated vortex operators. So let me now come to kind of the adaptation of these rules to the purely closed string amplitudes on the disk. There have been earlier calculations of 3-point functions of 1 closed string and 2 open states in type 1 theory by Alenka and collaborators. However, this kind of avoids a subtlety that you only have if you have only closed strings that I come to in a moment. So concretely, we are looking at type 2b with dp branes along the first spatial directions. The closed string vortex operator now lives in the upper half plane. So this is what I actually mean with disk, the upper half plane. And in order to deal with the right moving factor of the closed string vortex operator, I employ the doubling trick that people also used in the calculation of disk amplitudes in the INS formalism. So this boils down to extending the X field, which lives in the upper half plane, to the whole complex plane. So in particular to the lower half plane where Z bar lives, you extend it by the values of X bar at the corresponding position. And in order to impose the correct boundary conditions, you have to allow for relative signs. So the correct boundary conditions at the real axis, you have to allow for relative signs depending on the direction, whether it obeys directly or Neumann boundary conditions. So this introduces this D matrix. And this doubling trick can be also applied to spinors. This was also already done in the RNS case there. It was applied to the spin field. And here this psi alpha with upper and lower index denotes an arbitrary spinor of these two chiralities. And we introduce the analogs of these D matrix here also for the spinors, which we denote by M and N. In the INS case, the authors related these to some products of gamma matrices, but we won't really need the concrete explicit form for these matrices. All we need are some relations between these matrices M and N and the D matrix, which can be read off from asking consistency of the OPEs. And if you use these relations, then you can express the right moving part of the vortex operators solely in terms of kind of the left moving field, which however we extended to the full complex plane. So you still evaluate it in the lower half plane. And effectively the only remnant or effect of the doubling trick that's left then is the presence of the D matrix. I mean, you have to multiply the polarization vector and the momentum with the D matrix. Otherwise, up to this modification, these right moving forms of the vortex operators are the same as the left moving ones or the ones of the open string, which I discussed before, how to integrate out the non-zero modes and then the zero modes. So we can use, using this doubling trick, you can really use the same methods. You can use the same contractions as before. You just allow for both holomorphic and anti-holomorphic arguments. Now I come back to this small subtlety I mentioned before. If you only have closed strings, purely closed string amplitude on the disk, the conformal killing group only allows you to fix 1.5 closed string vortex operators. Yeah, so if you have one closed and two open, you can fix one closed and one open. But here you can not do that if you only have closed string vortex operators. And what we argued is that the way to proceed is that indeed you can fix one of the closed string vortex operators here in this example to I, And for one, you should use this mixed representation of the closed-ring vortex operator, where one factor here, in this case, the left-moving one, is taken to be of the unintegrated form, and the other one of the integrated form. I call it in the form, the unintegrated form for this V0. It takes exactly the same form, but note that it does still depend on a variable y, which you are still integrating over. But this is kind of reminiscent also of what happens in the RNS formalism. But we showed this really explicitly by following this nice paper by Hugeveen and Skandaris, who coupled the pure spinor string to topological two-dimensional gravity and then fixed the gauge in the usual BIST way. I should also mention that these mixed vortex operators for closed strings were discussed in the literature before, but as far as I know, at least, they were not used really to perform explicit calculations. So now let me come to the applications to the 2- and 1-point functions. First, the 2-point function. Here's really just the application of this formula, where we don't have these terms. We have this fixed closed-ring vortex operator, and this one in the mixed form. You just plug in the forms that I showed you before for the unintegrated vortex operator and the integrated one. You perform the Wick contractions. You get the usual Kober-Nielsen factor. And then here you have these, in the numerators, you have the kinematic factors, which arise from the zero-mode prescription. So after integrating out all the non-zero modes, you end up with expressions which contain 4 of these superfields multiplied. Oops, oh, sorry. So there's a sum of 2 terms for D1, similarly for D2 and D3. And now, as I mentioned, you have to expand all these superfields now in a theta expansion. And you have to project out the term which contains exactly 5 thetas. I mean, all of these anyway have 3 lambdas. And this is relatively tedious, and we used the computer program Cadabra by Peters, which is very well suited for this kind of calculations. The result that you obtain in this way is given here. The details are not so important. The gamma is a gamma function, q squared and t are these scalar products of momenta. Little a1 and a2 are given by these kinematic expressions depending on the momenta and the polarization tensors. Again, the details are not so important. What I want to stress is that you can get, again, the same result as for the RNS calculation. Quickly, the 1-point function, there has been earlier work in the bosonic theory and in the RNS case in the 80s. For the pure spinor, there seems to be an obvious puzzle here, because there are at most 2 factors of lambda if you use the unintegrated form of the closed-ring vortex operator. But luckily, there's a way out, because as we learned from this very interesting paper from Nathan from 2016, there's an alternative zero-mode prescription, which can be used equivalently for higher point functions at tree level. But which seems to be necessary to use it for the 1-point function. And this corresponds to the only alternative scalar element of the Q cohomology, which is just 1. So here the prescription is that after integrating out all the non-zero modes, you should take the terms which don't contain any lambda and any theta. So that's why if you calculate now the 1-point function, you should start with the form of the integrated vortex operator, which didn't contain any lambdas to begin with. But now, if you still integrate over the whole upper half plane, you have to divide by the volume of the conformal killing group, which of course is infinite. So the solution is the same as in the RNS case. You can fix the position of this to, for example, z equals I, and just divide by the volume of the subgroup, which leaves this invariant, which is given by this. So if you take this matrix and perform the fractional linear transformation, it indeed leaves I invariant, and this has finite volume. This is a result that we get then when we integrate out the non-zero modes and the zero modes. And this is indeed what you obtain, at least the structure, if you linearize the DBI action. So this is exactly what you get for gravitons.
Michael, I'm sorry, I forgot. You did speak for 25 minutes. You should try to wrap up. I'm
yes,
sorry.
No problem. I'm done in at most 1 minute.
Yes.
No problem. Thanks. So I just want to mention that there is an alternative approach to this question here due to Kashyap, which appeared pretty much at the same time as our paper, where he introduces an auxiliary field, which gives you the missing factor of lambda. So I come to the outlook. Obviously, it would be interesting to generalize this now to Ramond fields and fermions, because this is where the real power of the pure spinor formalism lies. Also, it would be interesting to generalize it to the projective plane. In the RNS case, the two-point function of closed rings was calculated by Garussi. And then in order to apply this at some point to the question that I raised at the beginning about the higher derivative corrections to the DBI action, we might have to go to higher endpoints. And this is something we already started together also with Stefan Stieberger. Okay, so this brings me to the end, and I thank you for your attention.
Thank you. Thank you very much, Michael. A nice talk. Please raise your hand. Yes, Harold.
Sorry, I was just clapping.
Oh, I'm sorry. Yeah, sorry. So please raise your hand for questions. If not, maybe I can ask a question. You said at the beginning that there was a heterotic type 1 duality argument for the 4-point graviton amplitude on the disk for its existence. Mm-hmm. Can you say it a little bit? What was the argument?
Yes. Oh, okay. Thanks for the question. I have some extra slides for that. So let me just quickly go through it. It won't take long, but let me remind you. Let me just close this. Let me remind you that in type 2, you have these two types of R to the 4 terms. These which are related or coming with the T8, which is an 8-dimensional tensor, 8 index tensor. So all the indices are contracted, and the epsilon 10 term that I mentioned before. And in type 2, these ones arise, both of them arise both at sphere level and at one loop level. Yeah, and the type 2b theory, I mean, type 1 inherits these terms from type 2b theory. Whereas in the heterotic theory, one knows that this epsilon 10 term only arises at tree level, at sphere level, not at one loop. Yeah, and so it only arises at one order in the perturbation theory, whereas at type 1, at least at 2 orders. So this is kind of a puzzle. How this can be compatible with heterotic type 1 duality. And this was then addressed by Green and Rudra. So what they propose is, and they give some arguments using heterotic M theory, what they propose is that you can express in the heterotic string the R to the 4 terms in terms of these two super invariants, J0 and I2. J0 contains both of the R to the 4 terms. And they propose that the coefficient of J0 is actually given by this Eisenstein series. Yeah, if you look at the dilaton dependence here, this gives you the sphere level term, and this one, the one loop term. But this would, and then there are these non-perturbative terms. But this would lead to having both T8 and epsilon 10 at sphere level and at loop level. And I told you in the heterotic, the epsilon 10 only appears at sphere level. So you have to subtract the loop level contribution explicitly again. Yeah, and that's done by this I2 term. And how does this help? This Eisenstein series is actually S-duality invariant. Yeah, and if you go through the mapping also of these terms, you see that this term actually maps, it's invariant under S-duality. It maps again to tree level and one loop, T8 and epsilon 10 in type 1, which you actually want. but this term maps separately. And that maps to a term which has the structure of a disk amplitude. So they predict, if this is correct, I mean, in order to save this heterotic type 1 duality for the R to the 4 terms, they predict this term at disk level, disk or projective plane.
I see. Thank you.
Mm-hmm. You're welcome.
There is another question by Dimitris.
Yes. Hi, Mikhail. Thank you very much. Really, really interesting and clear talk. So I was wondering, these mixed vertex operators seem very curious. So I wanted to ask, is there a well-defined gauge slice that picks these out, that splits a fixed, that takes you from fixed picture to half fixed, half integrated?
Well, I mean, as I said, we really followed the procedure of Hugeveen and Skandaris, who are performing a BSD gauge fixing, yeah, and this was the outcome that we found. I mean, first of all, it was kind of symmetrized.
Can one derive it from the fixed picture vertex operators? Can one derive it from the fixed picture vertex operators by choosing the path integral measure appropriately?
That I'm not sure.
It seems very strange.
I mean, as I said, I think it's similar for the in the RNS formalism. Yeah, there you have to fix the closed string vertex operator, right? But it's not really fixed. I mean, you get only one factor of the C ghost, and you still have to integrate it, but only over a real variable. I think you have the same question also in the RNS formalism.
Somehow, yes, you need to choose the, I don't know what formalism you want to use, but all the Beltrami differentials or the transition functions somehow to split the fixed into half split, half integrated, half fixed, half integrated. Mm-hmm. Maybe a choice of Beltrami differential will do this. Maybe a choice of transition functions. Maybe I don't know what formalism you want to use, but it must come down to some kind of choice like that. I think. I mean, in order for this to make sense. Mm-hmm. Which is very, very, very interesting. Mm-hmm.
I don't have much more to say about this.
Okay. I guess
Emilian, you are muted. Yeah.
Yes.
Sorry.
No, I was just saying maybe you should just have a very short last question. Nathan had a. I'm sorry to interrupt, but.
So I just had a comment. I mean, I think even for the bosonic string, it's just like peeling off a C ghost. That's the only. So you can get it from the integrated by, I guess, taking Q on it, either Q left or Q right, and just it's a total derivative of something, and it's a something. That's what you get. So I think it's similar to the bosonic string. I don't think there's a mystery.
Right. I agree.
I'd like to ask you more about that, Nathan. Maybe in the discussion session.
Yeah, sure.
Great. Thank you.
Okay. So thanks again, Michael, for the nice talk.
Mm-hmm. Yeah, you're welcome. So now
we should probably, yes, please stop sharing. And the next speaker is Rajesh Kopakumar from ICTS Bangalore. And the title, as far as I know, is From Fields to Strings and Back.
Yeah, thank you very much. 1 second, I am a little bit, I can't seem to find my screen to share. In the Zoom one, that's a little funny. It's not showing the
middle of the screen, no, down.
Yeah, it was. Maybe it should be in the same window, or I think.
At the bottom.
Yeah, no, I think it's just the window in which my talk is not the same as the window, the Zoom window. So, okay, let me try now. Yeah, I think that should work.
Right, it does, yeah.
Okay. So sorry about that. And so I'd like to thank the organizers for inviting me to speak at this nice meeting. So I will give a somewhat broad brush overview of an approach to understand or even derive ADS CFT from a fundamental level. This will be much of the recent work that I will talk about is in collaboration with Matthias Gabardil. I will also mention some recent works with my student Pranabesh Moiti and Matthias's student Bob Knighton, whom you will be hearing next. So, the question of how exactly large N quantum field theories reorganize themselves into theories of strings has been with us since almost 50 years now. We learned through ADS CFT that deep brain physics indicates that in some sense, open-closed string duality is the underlying reason, but that's in some sense, as we heard from Shi yesterday, a little too schematic. I think, like she mentioned, perhaps string field theory has a role to play here. But what I will be describing will be more an implementation of the spirit of open-closed string duality and not so much the letter. And it will be, but there will be points, and I will try to bring out some of the points where I think it connects to string field theory. So the basic mechanism, of course, of open-closed string duality, we believe, is that an open string theory in which the holes close up, and when you have a large number of D branes, the back reaction alters the geometry, and you have a closed string theory on a different background. But in the usual setup, especially where you're looking at the gravity limit, which is at large values of G string times N, or the Toft coupling, this is very difficult to see. And this has been one of the main stumbling blocks why we haven't been able to see how general gauge string duality is beyond those examples that we get from D-brain constructions. So that's one reason for me to try to understand this sort of in a more at a more basic level. So in some way, you can distill the parameter space of ADS CFT into two dimensions, where one dimension, the vertical dimension over here, measures the quantumness of the string theory, or is in terms of 1 over n, it's the deviation from the large n limit. So G string translates into 1 over n. So this is the quantumness axis, and this is the stringiness axis, the horizontal one, which measures which you can think of either from a gauge theory point of view in terms of the Toft coupling, or in terms of the string theory point of view as the curvature of the background. And typically we are focused here on the classical gravity limit, and most of the work in ADS CFT has been there. And what I will focus on here will be the other corner where we understand the field theory better, because we are at weak coupling, and but that corresponds to a highly curved or a tensionless limit, definitely a very stringy regime. But the nice thing is that we have a perturbative quantum field theory description in this corner, and we just have a finite number of Feynman diagrams or holes from the open string point of view to sum over at strictly zero coupling. And there is, of course, a well-defined genus expansion as well. And you can treat interactions perturbatively like you do in textbook quantum field theory. So we will focus mainly on a couple of test cases of this, looking at this corner, the case of ADS3 CFT2, where the dual is a free symmetric product CFT, and then I'll touch upon recent works on ADS5 dual to free super Yang-Mills theory. So operationally, for me, getting a connection between the two sides is one where where we understand better this part of the dictionary of ADS CFT, namely one which relates gauge invariant correlators of this of the field theory on the left-hand side to perturbative string amplitudes on the right-hand side, and the equality is one between single trace gauge invariant correlators, and we'll work in Euclidean space defined on the boundary of, let's say, ADS, which is a d-dimensional sphere, and we'll pick out the genus G contribution in a large N expansion, and the claim is that this is equal to some perturbative string amplitude, which you would expect to be some correlator in a CFT, an endpoint function in a CFT, and integrated over the moduli space. But of course, when I write something like this, this presupposes that there's a dictionary between the states themselves, that there's a correspondence between the single trace gauge invariant operators and these physical vertex operators of the string theory. In other words, that there's a matching of the spectrum. So of course, you need to have a string theory which reproduces this spectrum of gauge theory single trace operators to be able to then try to make this connection. But supposing you do have this correspondence of matching of the spectrum on both sides, then in principle, what I want to emphasize is that in principle, both sides are autonomously well-defined. The left-hand side is well-defined as a fixed point of a quantum field theory, and the right-hand side, in principle, at least if we can understand it, if we assume that there is a perturbative two-dimensional CFT that describes the string theory, then this side should be well-defined as well. And there is a mathematically well-posed question of whether we can make this equality same, or even in some sense tautologize it, make it sort of manifestly equal to each other. But in doing so, you might have felt that there's a potential asymmetry in the two sides, because it seems as if it's easier to go from the right-hand side to the left-hand side because you have to integrate over something, integrate over a correlator over this moduli space to get this. So it almost seems as if the right-hand side has sort of more information, whereas whereas to go from fields to strings from the left to the right, you need to reconstruct a worldsheet integrand, and that's not unique. But one of the things I would like to emphasize is that there can nevertheless be a canonical or a natural form for the correlator on the right-hand side, and I will try to describe one such way to recast these QFT correlators into stringy correlators. And in fact, this, what I just said, is a little misleading, because in some sense, you actually have the same sum on both sides, as I will try to bring out. That the basic idea is that there's actually a sum over distinct world line topologies in the Feynman diagrams for large N theory, which we, of course, have implicitly sort of hidden here on the left-hand side when we just written down the correlator. But if you evaluate it in a perturbative field theory, this is a sum over distinct Feynman diagrams, and that we will see is actually the same as the sum over the distinct worldsheets after gluing up the double lines of the field theory. And there's a canonical prescription to do that. So in some ways, the slogan will be that each Feynman diagram, so there's a sum over diagrams, and each diagram actually will correspond to a closed worldsheet, meaning a point on the moduli space of the closed string worldsheet. And this exploits something which is familiar to string field theorists, the so-called Strebel parametrization of the moduli space. And this way of associating Feynman graphs to closed string worldsheets is in some ways a refinement of Toft's idea, who assigned, of course, a genus, as we all know, famously a genus to Feynman diagrams, which we would associate with the genus of the dual worldsheet. But now we are sort of refining that further and going point by point in moduli space, so to say. And this way of, which I will say a little bit now, of associating to each Feynman graph a closed string worldsheet is in some ways an implementation of the spirit of open closed string duality, which will consist of gluing the 't double line strips, which are denoted here, gluing them in some canonical way using the Strebel parametrization into closed string worldsheets. So this is another way to pictorially capture that. So if we start from a field theory which correlator, and let me think here of a 4-point function where I have 4 insertions, actually 3 are shown here, the Z1, Z2, Z3, and there's one at infinity. And these double lines are the Wick contractions that you can have. So it's a particular Feynman diagram that contributes to a gauge theory correlator, and there's a composite operator, there are multiple Wick contractions. And so this is the field theory diagram, and the idea is that you glue up these into something which is equivalent conformally to a strip, just like we had over here. And now it's a fat strip that is, and the fatness is determined by the number of contractions. And you glue up these strips. So each of these diamonds over here is conformal to a strip, and it's these original diamonds. And this, the resulting picture that you get of a surface will actually is the sort of the Strebel construction of the moduli space of a closed string, and the insertions of these operators will be at the poles, and there will be the points where the strips are sort of glued are zeros of this Strebel differential. So the Strebel differential is something perhaps familiar to many of you. It's a very beautiful quadratic differential that's present on any Riemann surface. It foliates the Riemann surface into these so-called closed horizontal trajectories, which are essentially trajectories on the Riemann surface which obey this condition, where phi is the phi dz square is the Strebel differential. And the Strebel differential in some sense foliates the Riemann surfaces into these disks. Each disk has a pole, as a double pole actually, at some specified the Mach points Zi, and these disks are separated by a sort of a critical horizontal graph, horizontal trajectory, which you can see over here, which is marked in, which joins these A's over here. And this critical graph is in some sense the dual to the Feynman graph that we started with. And the idea is that the Strebel lengths, which are sort of defined as the integrals of the Strebel differential along these horizontal trajectories, these are proportional to the number of Wick contractions between the two different vertices, which are, I mean, the two different points that are connected by the dual edge. And at least for large numbers of Wick contraction, this seems to be borne out in the explicit examples that I will mention. Now, those of you who are familiar with the Strebel parametrization of moduli space would think that these lengths have to be arbitrary, but actually them being proportional to integers localizes them on moduli space. And we will see this now, or at least I'll mention how this is seen in explicit examples. So this tensionless limit of the ADS3 CFT2 correspondence is a test case where we can understand this much better. And this is the claim that the string theory on ADS3 times S3 times T4 with 1 unit of NS flux, so that's the minimal curvature and with the NS flux is equivalent to a symmetric product free orbifold CFT in the limit that you take n to infinity. This is something we showed in a couple of papers, how the spectrum matches and how you can match the correlators. In fact, this is a case where you can actually try to see how the picture that I just sketched for you is realized, because correlators on the left-hand side actually are known from in the symmetric orbifold CFT. They are specified by branching data involving the points x's and the twists of the orbifold. The w's are integers specifying the twists or branching, and the correlators are computed in terms of branched covering maps from this space-time S2, where the boundary CFT lives, to a covering space, which we now can identify with actually the worldsheet. In fact, to each such covering map, you can actually associate Feynman diagrams, very much like in Yang-Mills theories. And for large number, for when these twists are very large, that's actually a case where you can make things are very tractable, and each Feynman diagram corresponds to a sort of a point on the moduli space where the treble lengths are indeed proportional to the numbers of the big contractions in those Feynman diagrams. So this is an explicit realization of this. And this was something we obtained in a paper last year. And through mapping the problem to a matrix model whose spectral curve actually quite remarkably gives the treble differential. Moreover, this actually even tells you what the integrand on moduli space is, and that comes out in terms of a very natural functional on moduli space, which is the area, the number go to action with in what we call the treble gauge, which is essentially the area of the worldsheet with the treble metric from this quadratic differential. So I was saying so far about how you go from fields to strings, and in this particular example, you can do that very explicitly, as I said. But you can actually close the circle, and for that you need to show how the worldsheet gives rise to this same kind of localization, this sort of localization to these points on the moduli space. And in fact, this is something we saw in paper with Lawrence, Eberhardt, and Matthias in 2019. And in fact, the integrand is given by, from the worldsheet, you see this interesting localization, which actually follows from more fundamentally, we now understand as following from a twister-like incidence relation, about which you'll probably hear in Bob's talk. So let me just, the ADS3, because maybe Bob will talk some more about this, I'll just mention some very salient features about the, so even if, so something that I just want you to take away is that the worldsheet theory in the tensionless limit of ADS3 is very strikingly novel. It firstly has a free field description despite it being very highly curved ADS3, and it's in terms of a supergroup Weisser-Minowitten model, which is at level 1, and it's a bit like SU2 level 1 having a free field description. And this free field description is in terms of twister-like variables, the ones I had in the last slide, which can be viewed as a set of bosons, the beta-gamma system of bosons and corresponding fermions. The other interesting worldsheet ingredient that is important in this Weisser-Minowitten model are these so-called spectrally float sectors, which are inequivalent sectors in this non-compact Weisser-Minowitten model. And it is these spectrally float sectors that give you all the twisted sectors of the dual orbifold CFT. And it is this free field description through this twister incidence relation that leads to this delta function localization on discrete points on moduli space. And there is a semi-classical worldsheet which lives on the boundary of the ADS3 and gives this treble-like area as its as the classical action. So this case of ADS3 having realized things very nicely, we decided to sort of take this take a sort of a very natural generalization of this to the case of ADS5, where you can consider a corresponding twistor sigma gauge linear sigma model involving the corresponding twistor fields for ADS5 or its boundary. And I will just mention a few salient points of this connection. But the nice thing is that this actually ties up with earlier works like on the ambitwistor open string theory for Yang-Mills amplitudes. So that was in some sense an open string version, as well as with the BMN picture for a light cone gauge string theory for ADS5 times S5 in a large charge limit. So this free field description is one in terms of twistor fields, like I said, which give a free field representation of the PSU 2,2/4 supergroup. And these come by linears of this, and you have to impose a certain constraint which projects out the U1, because you actually get U 2,2/4. And the crucial ingredient of spectral flow that we had earlier in the ADS3 case is present here as well. And you can consider these spectrally flowed sectors. In some sense, it's sort of very similar to analogous to the ADS3 case. And what the spectral flow does is essentially you consider a set of fields which are in which you kind of shift the mode number, and you define new representations with a new vacuum which is annihilated by these tilde modes, which means that in terms of the original modes, we have sort of non-highest weight affine representations. And it is these that from which you can now generate new sectors of your worldsheet theory. And so for each of W, okay, thank you. So for each W, we have a Fock space which is built out of a finite number of wedge modes, which are these twistor modes lying. For each W, there is a finite set of modes which lie in this range, which act non-trivially on the vacuum because of the spectral flow. And then there are out of the wedge modes, which are sort of the usual negative modes. But notice that there are positive modes which do not annihilate this spectrally flowed vacuum, and this is very crucial. For W equals to 0, of course, no spectral flow. That's the usual NS sector. W equals to 1, you get you get 0 modes, and that's the Ramon sector. But for any W greater than 1, you have a finite number W modes over here, and the W equals to 1 sector is actually very special because it generates the so-called singleton representation of this PSU 2,2/4. I just want to just throw it out there that this W in some ways plays the same role as P plus in light cone gauge. So in some ways, this is like a covariantization of the BMN picture. But the main claim is that once we have this worldsheet theory with these twistor fields, that in an appropriate physical gauge, you can actually gauge away these out of the wedge modes, and that I mentioned over here, these all these modes, and you're left with only these modes acting on the Fock space, and so you're effectively left with sort of W bits. This perhaps follows from a larger extended worldsheet supersymmetry, just like as the analogous statement in ADS3 seems to follow from an underlying n equals to 2 worldsheet supersymmetry. So on this Fock space, you actually have some residual physical state conditions, again, a bit like in light cone gauge. You have, there's an L0 now, it doesn't annihilate the state because these are only the L0 of these physical modes. It's a bit like, again, in light cone gauge where the transverse modes, the L0 is proportional to P plus, which in our case is W. So there's very analogous to that. And then there's the constraint that I mentioned that you have to impose. This condition is, both are very physical conditions. One is effectively something that implements cyclicity on these W bits and a sort of a discrete translational invariance. This condition B is one which says that each individual site you effectively have a singleton, and you can make this manifest by doing a sort of a discrete Fourier transform. So what the upshot is that once you have imposed these residual conditions, the gauge invariant spectrum of single trace operators in large n equals to 4 Yang-Mills is sort of reproduced on the nose, because what these conditions do is effectively these W bits generate, once you impose the second constraint I mentioned, it just takes singletons and tensors them W times, and then the first constraint imposes cyclicity. And this is how you build up gauge invariant single trace operators from these single letters of Yang-Mills theories. So the spectrum comes out in a very neat way in this way. And one can actually go ahead now, once you have the spectrum, as I said, you can look at correlators, and the generalization of the generalization to twistor space of covering maps is something that's currently being worked out. I think there's a very nice but more involved picture here. But when all the points lie on a plane, then the situation is very much like ADS3. And in that case, you again see that the Strebel differential gives actually very neatly the Yang-Mills propagators with the number of big contractions. And you see that very similarly to the ADS3 case by going to the Strebel gauge. So this was, I realize, probably a little quick, but I'm happy to go into details in the discussion session. But just to summarize, I mean, we've exhibited these test cases, most notably the ADS3 CFT2, and we're beginning to see the same ingredients in ADS5 CFT4, where you can actually carry out this program of reassembling large N theories into string theories. And you could actually close the circle the other way around, because there was a tractable worldsheet description. So this holds out the hope that we can use this general program for general large N QFTs. But from a point of view of string field theory, I think, well, this is a more broad point about there being an underlying topological string description, but the Strebel parameterization and the Strebel gauge is something I think which cries out for a more a better understanding. It's in some sense some very singular gauge that you can choose, but it's interesting because it gives rise to Feynman diagrams of the field theory. So this, I think, is something where you could actually make contact. Furthermore, I just want to mention the string field theory community that I think here is, at least in the ADS3 case, where we now understand very well with 1 unit of NS flux, we sort of have the simplest example of a non-trivial, non-flat space background where with a concrete worldsheet description, which, and in fact, it's a free field description, and constructing a string field theory for this background, I think will be very useful, especially to understand non-perturbative effects and how you can actually go understand ADS beyond the large XP. Sorry, and for going over time.
So thank you, Rajesh, for a nice talk. Questions, please. Just raise your hand in the chat. Yes, Igor.
Yeah. Okay.
Thanks for the talk.
Oh, Barton. Okay.
Oh, well, Igor.
Just one point. you essentially look at the perturbative aspect of the mapping. That is, you mapped the G-loop string with the G-loop perturbation theory of Yang-Mills theory. So the question is,
yes,
it's somewhat obvious. What about the non-perturbative effect? For example, the 16 gauge Genus correlator is non-vanishing just because of the instanton. So
absolutely, absolutely, exactly. And this is what I had in mind when I had this last point on the outlook, that I think to understand these non-perturbative effects, you have to go beyond the perturbative description that we have for the worldsheet CFT. And this, I think, is something which should be very doable because it's a free field description, and to construct the string field theory and to do the sort of things that we've heard recently about the instantons in flat space, I think we should be able to do the similar things here as well, and precisely get the kind of amplitudes you mentioned. Yes, so I think that's a very interesting and but challenging question.
Okay, thanks.
Barton?
Yeah, just a comment and a question. That's quite fascinating, those treble differentials have made out appeared in here, because the connection with string field theory, in fact, is very clear. In the classical closed string field theory, the string vertices are, in fact, treble differentials. It's only when you approach the boundary of moduli space that they differentiate from treble differentials. So the new GNs, the vertices are in fact treble differentials. But now that so you, rather than landing on the worldsheet theory, you could perhaps land on the string field theory.
Yeah, yeah. So that's what I think. But but I think it would be interesting to understand this in more detail, which I think, so I definitely think there is a relation along the lines you mentioned, but I don't completely see all the pieces, but maybe you do.
Well, one question that comes up immediately, I don't know what you mean by the area of this treble differential, because
yes,
these treble differentials have infinite area. And
yeah, so exactly, that's a very interesting question. You have to regulate it. So precisely what we see in the simple examples is that these strips, as you said, they have infinite area because they're like vertical strips, but you regulate it, and the regulator is precisely corresponds to the short distance regulator in the field theory. And in the examples that we have, that regulator comes out as the multiplicative renormalization of the gauge theory correlators.
This regulator, the one we used in string field theory, the one of Teichmüller reduced area, I'm not sure.
Okay, at least the way we are approaching it, so the Streble metric, let me just say, since you asked also, the Streble metric is essentially the locally flat metric that you get by taking the modulus of the Streble differential. So you take the modulus of the Streble differential, it's locally flat, so the area is essentially the usual area, but you impose a cutoff on, I mean, you can think of these as strips, and you cut off the strip at some large length. And so that's the regulator we are using. So the infinite strip just becomes a rectangle.
I see. Is there, as you move in moduli space, is there a constraint that tells you that the total circumferences of the strips or the cylinders are constant?
Yes, in fact, they are equal to W. So each vertex, if I have an operator with W bits, so in these correlators, the W's, these are the residues of the Streble differential at these insertion points, at the dual points. So, so that's the branching data as well.
Great, thank you.
Okay, I don't see any question anymore. So thank you again, Rajesh, for a nice talk.
And thank you.
We go to the next speaker, which is Bob Knighton from ETH Zurich. And the title is ADS CFT at all loop borders.
Great. So I can just share my screen now. Yep.
Yep.
Great. All right. So first, I definitely just want to say thank you to the organizers for inviting me to speak. And I also do want to apologize in advance if my internet cuts out halfway through this. Apparently, the university decided that this would be a perfect time to work on all of the internet. And so there might be a 15-minute interruption in my connection at some point, but we'll see. So I want to talk about something that's very related to what Rajesh just talked about, but sort of in a more specific example in this ADS3 CFT2 example. Because this is an example in which we can compute correlation functions in the ADS3 string theory to all loop orders and really do get a handle on why these are related to dual CFT correlation functions. So first, just to give a very cartoony picture of ADS CFT to sort of set the scene. So in ADS CFT, you can consider anti-de Sitter space cartoonishly as a solid ball, and then you consider the boundary, or a CFT living on the boundary. And you can consider correlation functions of operators inserted on that boundary, and they should, in a sense, correspond to worldsheet correlators that are computed in the bulk. And on the ADS side, yes. So on the ADS side, you compute this in the standard string theory way, where where string theory graphs are sort of organized into a genus expansion with a coupling given by the string coupling. And in the same way, on the dual CFT, there's also a genus expansion which comes whenever your dual CFT has a large number of degrees of freedom. So in particular, your dual CFT is going to admit a genus expansion where now the genus is thought of as the genus of the Feynman graph. So the minimal surface that you can embed your graph on. And for a real stringy derivation or a real stringy proof of ADS CFT, you want to show, at least perturbatively, that for any given ADS and its dual CFT, that these observables correspond to each other at all orders in the expansion. And then you identify the string coupling with being roughly 1 over n, or in some cases, 1 over square root of n, which I'll talk about in a minute. The main problem is that ADS CFT is a strong weak duality. So whenever one side here is tractable, the other side isn't. So there's sort of two regimes we can consider in which one side is tractable, and then we sort of have to deal with the fact that the other side is not so tractable. So the two regimes you can consider, and these are both in the large and low string coupling regime, which Rajesh just talked about. The possibly tractable regimes, so the first one you consider the regime in which the string length is very small compared to the space-time geometry. And in that regime, string theory essentially reduces to a supergravity approximation. And so you can use all the tools of general relativity or in QFT uncurved spacetime to compute certain correlation functions. But the drawback is that the dual CFT in this regime is very strongly coupled. And so only very special protected quantities can be calculated analytically. Now, on the other hand, the opposite regime is one in which the string length is as large as it can be. So on the order of the space-time curvature, or possibly bigger. And then in this case, the bulk theory is going to be very stringy. And so you can't really rely on semi-classical supergravity. But the dual CFT is then weakly coupled. So you can calculate things perturbatively on the dual CFT. And traditionally, most ADS CFT calculations, most checks of ADS CFT has been done in the supergravity regime. However, there is an advantage to the opposite tensionless regime, which, as I mentioned, is that the dual CFT is weakly coupled. And one can ask the fairly innocuous question, If I have a free dual CFT, can there be a sense in which the worldsheet theory, can I ever hope for that to be described by a free theory? And this turns out to be the case in a very special example of ADS CFT. And this particular example relates what we're going to call tensionless string theory on ADS3 cross S3 cross T4 with a dual 2D CFT, which is the symmetric product of a sigma model on T4. And then this correspondence is going to hold in the Lagrangian limit, where here n counts the number of copies of T4. And this can be thought of as sort of a lower dimensional analog of ADS5 CFT4 in the free field limit, which Rajesh talked about in quite a bit of detail earlier. And the thing that makes this particular incarnation so special is that both sides are under really good analytic control. In particular, you can calculate many quantities exactly. So you can calculate the spectra on both sides, for instance. And these can be shown to agree. And you can also calculate certain classes of correlation functions. And these can also be shown to agree. But what I want to do in this talk is try to convince you of a simple geometric picture which relates these two, and which will hopefully also be generalizable to ADS5 CFT4 in the future. But before I can do that, I sort of have to introduce the two big players. So first I'll start with the symmetric product CFT, since it might not be familiar to many of you. So the symmetric product CFT is sort of a natural way to take a CFT X and then from it generate a CFT with a large number of degrees of freedom. So you consider a conformal field theory X, which we'll call the seed theory, and then you take n copies, and then you orbifold by the action of the symmetric group. So the fundamental fields in this theory are going to be n tuples of fields in X, and then you say two n tuples are the same if they're related to one another by a permutation. And in particular, if X is going to be a sigma model on some manifold, then the symmetric orbifold of X is a sigma model on the symmetric orbifold of that manifold. And to give a very concrete example, you can consider taking the symmetric orbifold of just the real line. So that involves, so say we want to do n equals to 2, that involves just taking 2 copies of the real line. So now we're on R2, and you identify points xy with points yx. And what you end up with is this lower triangular space-time, or this lower triangular target space. And this is generically what the symmetric orbifold is going to look like. Now, as with any orbifold, states in the symmetric orbifold are going to be labeled by conjugacy classes of the orbifold group. So in particular, a state in the symmetric orbifold carries some label, which we'll call the twist. And this is labeled by some conjugacy class in the symmetric group, which is some permutation determined by its cycle type. And in particular, we want to focus on single cycle permutations. So those whose cycle type is only one non-trivial cycle, and that cycle has length W. And this is called the W twisted sector. And these states are special because they're analogous to single trace operators in gauge theory. And on the string theory side, they correspond to single string states, which are the only ones you're going to be able to see from a worldsheet description. So now that we kind of have an idea of what the states in this theory look like, we need to understand how to compute correlation functions if we ever hope to match them with those in ADS. And I can't fully convince you of this in the time I have, but there's a very beautiful construction of these correlation functions due to Lunin and Matur. So if you can consider correlators on the sphere, so you insert some operators on the sphere, they have certain twists, and they're labeled by certain seed CFT states, then in order to construct the correlation function, what you can do is consider, instead of working on some
Bob, we have a problem. We don't hear you. At least I don't hear you.
Yeah, it's also frozen for me.
He should use his iPhone if he has.
Where did I leave off?
So it was the next slide when you were still on the, I mean, you are explaining that you add to this covering space and.
Okay, yeah, so I'll just start over with this then. Great. Again, sorry for the interruption. So if you want to consider correlation functions in the symmetric orbifold, the thing you have to do is consider instead correlation functions of the seed CFT on these covering spaces, which cover the sphere a certain number of times. And in order to get the right analytic behavior, when you pull back from the sphere to these covering surfaces, these covering maps between the two surfaces have to satisfy certain criticality conditions. So in particular, this covering map has to map certain mark points on the covering surface to the sphere, and then near those mark points on the covering surface has to have some critical points of order W. And this turns out to be the correct analytic behavior in order to pull back these twisted fields to the covering surface to just reduce them to correlation functions in the seed CFT. And this is a very concrete example of a genus expansion in a conformal field theory, where now you can think of these covering surfaces as being your Feynman diagrams, or equivalently, you can think of these holomorphic maps as being your Feynman diagrams. And the genus of that diagram is simply the genus of the world sheet, or the genus of the covering space. And so this gives you a very concrete example of a genus expansion in a gauge theory. And if we want to be able to show that this is equal to some string theory on ADS, you want to be able to make this genus expansion manifestly equal to the one in string theory. So before I even introduce this tensionless string theory on ADS, let's just assume that these correlation functions you compute in the symmetric orbifold CFT are equal to some correlators that you can, or some amplitudes you can compute from the string theory side. So from the dual CFT, we're able to express these correlation functions as a sum over certain discrete set of. Whereas on the string side, you can consider a correlation function on the world sheet, and we'll take vertex operators to also carry some labels, which will correspond to these twists. And these are the spectral flows that Rajesh was talking about in his talk. And then when you calculate the correlation function on this world sheet, you then integrate over the moduli space and sum over the genera, and you want to demand that these two things are equal. But the right-hand side is an integral over a continuous set of surfaces, while the left-hand side is an integral, or is a sum over a discrete number of surfaces. So a very natural way to get these two things to manifestly equal each other is if the string theory world sheet localizes, or the string theory world sheet calculation localizes to certain points in the moduli space, which I've marked by these gammas here, for which the world sheet is the covering space that we consider in the symmetric orbifold. In which case you should think of the string world sheet as being this covering space that's being used in the calculation of symmetric orbifold correlation functions. And this goes back to Pachmann, Rosselli, and Razamat in an analysis they did in 2009. But at the time, it was very much a, wouldn't this be nice if there was a string theory that had this property? But as it turns out, there is one. But just to get a little bit more of a cartoony picture. So now instead of having some nebulous auxiliary surface that's covering the base space of the symmetric orbifold CFT, we really think of the world sheet as covering the boundary of ADS that the CFT lives on. And in a cartoon picture of what this looks like from a string scattering perspective is that you have string states which are emitted from the boundary and then sort of stay near the boundary the entire time. And as such are sort of glued to the boundary, and this map gamma is what glues them to the boundary. So enough philosophizing, what actually is this ADS3 string theory? Well, as Rajesh briefly mentioned, the tensionless string on ADS3 cross S3 cross T4 is based on a supergroup Wess-Zumino-Witten model, PSU1,1/2, where you take the level K to be equal to 1, and then you take the T4 to sort of come for the ride. And PSU1,1/2 at level 1, as any supergroup, has sort of diagonal bosonic degrees of freedom. So you have an SL2R degree of freedom, which corresponds to your ADS3, an SU2 degree of freedom, which corresponds to your S3, and then supercharges in the off diagonals. And as it turns out, specifically at K equal to 1, this supergroup admits a free field realization in terms of 4 spin-half bosons and then 4 spin-half fermions on the world sheet. So you get 4 free fields, or 8 total free fields, which when you take certain bilinears in them, you get the corresponding components of the PSU1,1/2 superalgebra. And states in this theory are going to lie in representations of PSU1,1/2 at level 1. And these states are going to be labeled by some number W, which is the spectral flow that Rajesh mentioned. And they'll carry some conformal weight. And they'll also carry an extra index X, which you can think of as being the position that the vertex operators emitted from on the boundary of ADS. And then there's going to be some T4 state, which you can think of as just sort of coming along for the ride. And in the end, you're interested in correlation functions of these states in the PSU1,1/2 model. So computing these correlation functions naively is a very difficult task, but it turns out that there's a very simple trick that you can use to show first that they do have this localization principle, but also, and I won't talk about that now, you can really constrain their form very heavily. And the trick is to take these free bosons that you can use to, or in the free field realization of PSU1,1/2, you take these free bosons and you insert them into whatever correlation function you want to calculate. And this physical subscript here is doing a decent amount of heavy lifting. Defining these correlators is a bit more subtle than I've made it out to be. You have to include picture changing and all this normal stuff, but once you've done that, you can simply introduce the free field into the correlation function, and this defines for you a function of Z on the world sheet. In particular, it defines you a section of a spinor bundle on the world sheet, but that's a technical detail we don't need to worry about. And furthermore, you know what the OPEs are if you work out what these states are in terms of the free fields. You know what the OPEs are between your free fields and these vertex operators. And from this, you can deduce some analytic properties of omega. One, you can deduce that omega, both plus and minus, will have poles of a certain order at each of the insertion points, just from the OPE. And based on the way that this X coordinate is defined, you can also show that a certain linear combination of these two fields will have a 0 of a certain order at these insertion points. And something that's a bit more non-trivial and has to do with this picture changing that I'm sweeping under the rug is that omega plus and omega minus have a certain number of shared zeros, which corresponds to the number of picture changing operators you have to insert. And given these 3 criteria, this turns out to be enough to completely constrain the forms of omega plus and minus up to a scale. And it turns out then, if you consider the ratio of the two, this defines a function on the world sheet, and you can ask what its analytic properties are. And it has exactly the same analytic properties as this covering map that you use to compute correlation functions in the dual CFT. Now, if such a covering map doesn't exist, so if the world sheet doesn't have the structure of a covering space to the sphere that you want, then something in this argument has to go wrong, because we're able to construct these omega plus, take the ratio, and get a map that has precisely the qualities that the covering map has. And the thing that has to go wrong is that the correlation functions you start with have to vanish. And so whenever a covering map doesn't exist, you're able to show that the correlation functions are themselves 0. And so this manifestly proves that that these correlation functions have to localize to the points in the moduli space where such a covering map exists. And with a little bit more effort, you can also show that using the same trick, and in particular this relation here, that when the world sheet correlators don't vanish, then you can constrain the HI dependence, so the dependence of the correlators on the conformal weights, and this also matches with the symmetric orbifold answer very nicely. And so that's the entire argument from the world sheet as to how the correlation functions on both sides really manifestly reproduce one another. So just to briefly summarize, in order to compute symmetric orbifold correlation functions, this can be done in terms of a geometrization of the problem, in which instead of considering these complicated twisted states, you instead move to a covering space and then calculate correlation functions on those spaces. And the difficult part of the problem then is finding these maps from some covering space to the sphere that have the right structure. But this is a well-known mathematical problem. And the tensionless string, this covering map arises by introducing these two functions on the world sheet, defined by the free fields, and the ratio is then exactly this covering map. And therefore you can deduce with a little more effort that the string theory correlation functions will localize on the moduli space. Now, this is all well and good for this particular case of perturbative states in ADS3, but as Rajesh just mentioned, this free field realization of writing the supergroup in terms of free fields on the world sheet, this has a natural generalization to ADS5, which reproduces the spectrum of free n equals 4 supergang mills. And so the question, which is very interesting, is whether you can use a similar geometric picture to compute correlation functions in this free field realization of ADS5. And that certainly is a lot more difficult, but we're currently working on that. And then another very interesting question is what happens when you introduce non-perturbative states into ADS3? So you have certain branes that exist in the bulk of ADS3. Do you get a similar localization condition? And so far, it seems the answer is yes. It seems that the covering map that you need to consider then is a map between surfaces with boundaries, where you think of the boundary as the location of the brane. So that is everything I wanted to talk about. So I just want to say thank you for your attention, and I'll open for questions.
Thank you. Thank you, Bob, for a nice talk. So questions, please raise your hand. Nathan.
Right. Do you have anything to say about higher genus or loop corrections?
Yes. So this argument holds at every order in the genus expansion. So at no point do I assume, or in our original paper, we did assume that we were on the sphere, but these functions here, these omegas that you can define on the world sheet, these are well-defined sections of a spin bundle on any genus world sheet that you have. So this argument that
you're doing the free theory, where's the genus coupling constant?
Yeah, so you can't really see the coupling constant at the order of this free field realization. This is sort of something you have to put in by hand by demanding that the genus expansion has the normal form. Or maybe I'm not understanding your question quite right.
You have two sides that you want to show are equal, but you haven't identified where the genus coupling constant is in the field theory.
Yeah, so in the field theory, the genus coupling constant is kind of hidden in this conformal transformation factor that you use to compute symmetric orbifold correlation functions. So I haven't explicitly written it, but it is sort of implicitly embedded in these factors that you use to weight different covering spaces.
Thanks.
Other questions? Maybe ask a last question. The D-branes effects on the CFT side should correspond to some non-perturbative effects on the, which kind of effects correspond to the CFT side?
Yeah, so on the CFT side, it really seems that these certain classes of D-branes in ADS3 correspond to considering a dual CFT that has a boundary. So now you consider boundary states in your dual CFT instead of, yeah.
Okay.
Yeah. So ADS3 with a brane now corresponds to some dual CFT with a boundary, which you can think of as where that brane intersects the ADS3 boundary.
Thank you. Okay, I don't see any further questions, so thank you again. And I leave Harold maybe to announce the probably coffee break, I guess.
I'm going to talk about the disk partition function in the string theory. This is a work done in collaboration with Lawrence Eberhard, who is also here at IS. And as the title suggests, today we are going to explore some very basic stuff about worldsheet approach to string theory. And this will be a very ground to earth talk. So let's begin. So why do I care about the disk partition function? The immediate and the short answer is that as a newcomer to the field, understanding this lower genus string partition functions is confusing and intriguing at the same time. They are intriguing and interesting because they are related to various quantities which, as a broad high energy community, we care about. For example, we expect the sphere partition function in string theory is related to some on-shell gravity action. And normally, if we have a black hole, then the on-shell gravity action should encode some information about black hole entropy. So ideally, we would like to have a scenario where we have a string theory with a target space where the target space has some black hole, and we would like to do some string theory computation which can essentially produce the black hole entropy. And for this kind of questions, it is very important to understand the lower genus string partition functions, for example, the sphere partition functions. So our project started initially to understand the sphere partition function, but it turns out that the sphere partition function is technically much more harder. So we looked at its nearest cousin, which is the disk partition function. And the good thing about the disk partition function is that the disk partition, if we can compute the disk partition function, it should be related. It can be related to the d-brane tension, and we already know the result of d-brane tension. So there will be a nice cross check of our method. So all the stuff that is on the green diamond here is the stuff which are intriguing, and which is why we are interested in this in understanding the lower genus string partition function. But at the same time, we have this red diamond where there are some confusing aspects to it. For example, in all this lower genus string partition function, naively they seem to vanish because of non-compact gauge redundancy. And if they vanish, then it's a problem because just minutes ago I said that it is supposed to reproduce some black hole entropy, d-brane tension, and whatnot. So let's first try to unpack the confusing elements of this thing. So to do that, we let us be concrete and let us start with a critical bosonic string. So this is given by a nonlinear sigma model with some target space. And furthermore, we assume there exists in the target space, there exists a flat direction. So in that flat direction, we basically have a free boson. So most of our calculations involves dealing with this action and proper gauge fixing this action and so on. So once we have this thing, we do our usual stuff, we fix the conformal gauge. But for the sphere and the disk, even after fixing the conformal gauge, there is a combination of wild invariance and diffeomorphism which remains unfixed. So for the sphere, it is basically this redundancy is given by the group PSL2C. So there are 6 conformal killing vectors, which keeps the sphere fixed, the metric of the sphere fixed. So this is PSL2C. And for the disk, we have a subgroup of PSL2C, which keeps the disk, the metric of the disk fixed, which is basically the PSL2R. So the question is, so the point is, when we have 3-point or higher point function, we want to compute the 3-point or higher point amplitude, we can use this PSL2C or PSL2R to fix the position of the vertex operators. So normally the vertex operator always appears in an integrated way, integrated over the worksheet. But then we can use the PSL2C or PSL2R to put these vertex operators at 3 disk points so that those integrals get killed off. And then we do not need to worry about the PSL2C or the PSL2 or this gauge redundancies anymore. But when we look at a worksheet with insertion of vertex operators being less than 3, 2, 1, or 0, then of course I cannot use up PSL2C or PSL2R. Like I can use up some part of PSL2C or PSL2R to fix the vertex operators, but there will be always one non-compact directions left out. And because there is a non-compact direction, naively you would expect that all the lower point function below the 3-point function vanish. But it turns out this nice expectation is not completely right, not right. In fact, a couple of years back, Harold, Huan, and Dimitri showed that the 2-point string amplitude for a flat space, flat target space in D equals 26, actually non-vanishing. In their case, what happens that there is a non-compact direction coming from the PSL2 or PSL2C in the denominator. There is an infinity in the denominator, but then there is also an infinity in the numerator coming from the Dirac delta function. And these infinities nicely cancel each other out to give a non-vanishing answer. So here, instead of looking at the 2-point string amplitude, we will focus on the 0-point case, which is the disk case. And here we will see the mechanism of finding, and again, here we will find a non-zero answer, but the mechanism is slightly different. Here, it is not exactly infinity getting cancelled by infinity. Rather, we will do some honest QFT calculation where we'll take the PSL2R group, we'll do some gauge fixing procedure, and we will land up with a finite answer. So let's move ahead and think about the disk. So as I was saying, the disk for the disk, the gauge redundancy is given by the group PSL2R, and PSL2R is nothing but SL2R/Z2, and the definition of PSL2R is basically given by this matrix A, B, B bar, A bar, with this defining condition that mod A square minus mod B square is 1. And on the unit disk, this PSL2R acts as a Mobius transformation, which is given by this. And the disk partition function is basically given by the ZCFT divided by the volume of the PSL2R, whereby ZCFT, I mean the partition function of the worksheet CFT. And you have to divide by the volume of the PSL2R because that's the gauge redundancy. So our first job is to understand the volume of the PSL2R. So how can we go ahead and calculate the volume of the PSL2R? So let's move ahead and think about the volume element. So there is a natural volume element that we can define on the PSL2R group. So this is an integral over these parameters A and B, both are complex parameters. And because you have to maintain this condition, you put a delta function here. Now, basically, you have to evaluate this integral, and just staring at this equation, you can easily realize that one can parameterize A and B by some function cosine hyperbolic and sine hyperbolic. And because you have mod A and mod B, you can also put in some phase factor here without any cost. So basically, we have 3 parameters, phi, psi, and x. The x parameter runs from 0 to infinity, so this is one non-compact direction. And this phi and psi are the angular variables. Phi runs from 0 to 2 pi, and psi runs from 0 to pi. And this pi comes instead of 2 pi because we are dealing with PSL2R, which is SL2R/C2. So once we have this variable phi, psi, and x, we can rewrite this volume expression in terms of the x, psi, and phi integral. Once we do this, the angular integral can be done very neatly, and this gives you 2 pi squared. But then there is an x integral left, and the x integral runs from 0 to infinity. And as you can see here, there is a cosine hyperbolic x times sine hyperbolic x, which goes like, for large x, goes like exponential twice x. So of course, this integral is divergent, like e power 2x, as x goes to infinity. So this is a problem, and this is why we naively expect the answer to be 0. But this is where this paper of Polchinski and Liu came about, and they figured out a way to subtract of the divergence. So what they said, that instead of doing the integral up to infinity, we cut off the surface at some x equals x star, and then we evaluate the volume inside the x star, and then subtract of some quantity, which is basically the extrinsic curvature on that surface, which is defined by x equals x star, and we subtract of this term. So this is somewhat like calculating the on-shell gravity action in ADS2, where you put a cutoff, you define some extrinsic curvature on the cutoff surface, and you subtract off some boundary term. So if you do this procedure, then you can actually complete this integral is finite, and so you do this subtraction, and then you take x star going to infinity, and then you land up with the finite answer, which Liu and Polchinski called the regularized volume of the PSL2R, which is basically a negative number, which is minus pi square over 2. So while this answer is correct and it gives you the right answer, but somehow we felt like the answer is a bit ad hoc. This approach is a bit ad hoc. So we wanted to do an honest QFT calculation, where the idea is we will take the PSL2R gauge group. We will use this gauge group to do some gauge fixing procedure. And then after doing an honest QFT calculation, the idea is we will again land up with this answer minus pi square over 2. And this does not involve taking any cutoff or anything like that. So with that in mind, we will go ahead and do the gauge fixing procedure. So just to briefly recall, how do we do the gauge fixing procedure? So generally, we have a path integral over some configurations x, and there is some, because of gauge freedom, because of gauge symmetry, like if we are integrating over all the configurations, we will land up with infinity because various configurations are related by the symmetry. So we have to do the gauge fixing procedure. And the gauge fixing procedure proceeds by choosing a gauge condition, which is f of xg being 0, and then inserting this identity in the path integral. Now, where this is the gauge condition, and this quantity delta is related to the absolute value of the Jacobian. Now, one of the key assumptions that goes in this prescription, this inserting this resolution of identity, is the fact that the gauge orbit intersects the gauge surface once and only once. So where by gauge fixing surface, I mean the surface defined by f of xg equals 0. So in most of the time when we are dealing with perturbative QFT, this doesn't really matter because we are only looking at some small neighborhood. And in the small neighborhood, it's true that the gauge orbit intersects the gauge fixing surface once and only once. But in our case, it is very important to take care of this issue and actually make sure that either we have to make sure that we choose a gauge so that the gauge orbit cuts the gauge fixing surface once and only once, or we have to invent some new ways to do it. So it turns out like we can understand this better in a more toy example, where instead of a path integral, we have a regular integral. And the analogous relation of this becomes this relation. So here you can think of a function f of x, this black line, you can think of this black line as the gauge orbit, and the red line as the gauge fixing surface, which is fx equals 0. So this y equals fx, I should have written here. Now the point is, if you consider, and so if you look at this integral here, so this delta of fx is like this delta of fxz, and this f prime x, the absolute value, is like the absolute value of the Jacobian. Now, of course, on the left-hand side, it does not give you 1, rather it gives you the number of times this black curve cuts the red curve. So basically, this is number of roots. Now, as you choose different functions, the number of roots can be different. So instead of 1, it will be a function. It will be a function of the functions you choose to do this procedure. And of course, you cannot insert this in the path integral. That's precisely the problem I was mentioning, because it violates the assumption that the gauge orbit cuts the gauge surface only once. But there is a way out under some suitable condition. So instead, you impose these conditions on your functions f, that as x goes to plus infinity becomes plus infinity, and as x goes to minus infinity goes to minus infinity. If you assume this, and if you forget about the absolute value here, instead if you do the integral like f prime x, then you see that it actually counts the root but with a sign. So for every brown dot, it counts +1, and for every blue dot, it counts -1. And because of this boundary condition, no matter how many times this function cuts the red line, it will the number of brown dots will be always 1 more than the number of blue dots. And that means this 1 is guaranteed for all kinds of function which satisfies this boundary condition. So the take-home lesson is that one can actually get rid of the Jacobian under some suitable condition and introduce this as a resolution to the identity. And here also another important point is that if I change the boundary condition here, then keep the plus minus sign, then there will be a -1 here. So that means the Jacobian will come with a minus sign as a resolution of the identity. And this will play a crucial role in our calculation, because we know at the end of the day, we had to come up with an answer which is -π²/2. And this will precisely be the source of the negative sign. So to move ahead, let's focus back to our problem, which is the gauge fixing of the PSL tour. So to do that, we start with a disk, and then we put the upper hemisphere metric on the disk. And because we are dealing with the free boson, we take the field X and do a decomposition on the, because it's on the sphere, we can do a spherical harmonic decomposition. And on the boundary of the disk, that is on the equator, we have some boundary condition in the Dirichlet-Neumann. Depending on that, we keep some modes or we throw out some modes. And the gauge fixing condition is nothing but choosing some appropriate modes and setting them to 0. So for the Dirichlet, we set x2 ± 1 to 0. And for Neumann, we set x1 ± 1 to 0. So as usual, when we gauge fix, we basically break the gauge symmetry. So that means there will be, so ideally, if we break the full gauge symmetry, then if we do a gauge transformation on this configuration, it will take me to some different configuration. But it turns out that this completely does not fix the gauge, rather there is a remaining U1. In fact, you can calculate and see that there is a subgroup of PSL2R given by this gamma alpha. So this subgroup actually is broken, and this takes you away from the gauge fixing surface, which is given by this. And there is a remaining U1, which is basically these diagonal elements. If you set alpha to 0 and put the diagonal elements to some phase, so this is the remaining U1, which is unbroken. But this is fine because the U1 is a compact gauge group, and so we can take care of the volume of the U1. So now the point is to find out the sign intersection number that I was mentioning just a minute ago. And to find the sign intersection number, we have to solve this equation for alpha. So in the next slide, I will try to unpack this equation. So what we are doing the following. So what do we mean by gauge fixing? Given any configuration X, we have to do a gauge transformation, and that chosen configuration then will lie in the gauge fixing surface. So the question is, can given any configuration X, can we choose a gauge transformation to reach a given gauge fixing surface. So to do that, we start with X. We do a transformation by this gamma alpha, which like moves me along the gauge orbit. We obtain this X gamma alpha inverse Z. So this is this, and then we project onto our particular modes, which the projection is done by these things here, this integral over the harmonic modes. And this being 0 is precisely our gauge fixing condition. So all we need to do is we need to figure out the number of solutions of this equation, some number of solutions for alpha, and we have to count the solutions in a signed manner. So we have to keep track of in which way it cuts the gauge fixing surface. And it turns out that this can be handled by the winding number. So you define some quantity, define this quantity appearing on the left-hand side as some V alpha, has a function of alpha, and this alpha variable also belongs to the disk, but this is the disk of the PSL2R. And then you can figure out the winding number of this V alpha. And from that winding number, you can figure out the signed intersection. So after some detailed complex analysis, you get to the result that the signed intersection number is related to the winding number. And for this specific thing, the winding number is -1. And this leads us, after all the dust settles, this leads us to the following identity, which we will insert in the path integral. So this is the regular piece, which is like the delta of f alpha x, which is the gauge fixing term. This is the usual Jacobian. This is the integral dg, which is the integral over the PSL2R volume element. And there is an important minus sign which comes from this winding number procedure. So we take this quantity and we insert this in the path integral. So,
5 minutes.
Thank you. So insert this in the path integral. So now the point is, without the gauge fix, so now for a second, forget about the gauge fixing procedure and think about the word-set CFT. It's a free CFT, so we can do the path. So basically, it's a Gaussian path integral of the over the modes XLM. So we can actually do it, and it's a finite number because we know how to regularize everything. So what's the effect of the gauge fixing procedure then? We basically insert this thing in the path integral. So that means if we are setting x2 plus minus 1 to 0, so the two mode integrals get omitted due to the delta function. And this Jacobian is nothing but a polynomial of finite number of modes. So which is given, for example, for the Dirichlet case, this is given by this thing. So all we have to, so comparing to the ungauged version, we basically are modifying some of the integrals by introducing these polynomials, and we are removing some of the integrals. And because everything is Gaussian, one can just do it by hand. And once one does these integrals, we land up with our precise answer, which is z disk equals z CFT divided by minus pi square over 2. And this is what Polchinski and Liu obtained by doing this cutoff procedure. But we feel that the way we did is much more rigorous and much in the way we learned basic QFT. So there are two more things I want to mention, that there are two more different ways in our paper we did, and we arrived at the same result. One of them was involving some different gauge fixing condition, which was del x 0 equals 0. And the other method involves slightly different stuff. There, what we do is that we realize that the x can be compactified with some direction x plus 2 pi L. And then there is a vertex operator which actually changes this capital L, this periodic identification parameter. And then one can relate the disk partition function with the 1-point function of this vertex operator, which changes the value of the L. So this is the marginal operator. And this and then one can use the PSL2R to gauge fix this vertex operator and compute the 1-point function, and again land up with the same answer as here. And in all these cases, this partition function, as I said, can be related to the D-Brent tension because of this following relation. So basically, and here you can see that the minus sign is important, because unless we have this minus sign, the tension of the D-Brent would have been negative. So to obtain a positive D-Brent tension, it's important to have this minus sign. So finally, I would like to, so this is what I wanted to say about the disk. And finally, I would like to conclude about by saying some open problem. So it seems like ideally, we would like to have a very good understanding, a similar understanding of the sphere partition function. But naively, it feels like the idea of gauge fixing by considering the spherical harmonic modes apparently fails for the sphere partition function. So all the things we have tried, most of the time we would not, either we are not able to prove that the gauge is admissible. And in cases where we are able to prove the gauge is admissible, we'll end up with answer, for the flat space, we'll end up with answer like 0 times infinity and so on. So is there any first principle calculation for sphere partition function? For example, can we prove that in the flat, like generally people expect in the flat space, because of PSL2C, the gauge, the thing is, the sphere partition function is 0. Can we prove that? And also we are thinking about similar kind of problems with the ADS3 target space, because for example, in the ADS3 target space, we do not expect the sphere partition function to be 0. We expect it to reproduce the boundary conformal anomaly by some means. So can we do some completely string theoretic computation where we will see the boundary conformal anomaly and so on? So in future, I would like to think more about the sphere problem. Thank you.
Thank you for a very nice talk. Are there any questions? Yes, Harold, please.
Yes, so I wanted to check for the sphere, because here, as you phrase it, it looks like you want to compute just the partition function of the sphere for some background. But like if we think what we do in general relativity, because here we would map this to the QFT on curve space with gravity. So here for the action, in fact, we have to consider the Gibbons-Hawking term, and then we also subtract when you want to compute the on-chain action, like some reference metric to get a finite result. So I would expect in principle that we will need to recompute difference in,
yeah, but I guess the issue is perhaps so generally in the general relativity, we compute the on-chain gravity action, we put a cutoff and calculate the extrinsic and define extrinsic curvature, and there is a boundary term. But in terms of, if you want to do it in string theory, then I believe you have to put that cutoff in the target space. And then it's not clear how to, at least not clear to me, how to do that in a very stringy approach, because then you have to do a path integral where your target space, these x coordinates have a boundary, like have a cutoff and so on. And even at all, whether it is consistent to put a boundary, put a cutoff like that in a string theory, whether it is wide symmetric or not. Because I guess in most cases, if you put a cutoff like that on the target space, the while invariance will be broken.
Okay.
So it's a conceptually difficult problem.
Because then I would still think that you will need to consider like the ratio of the background you want to work with, for example, Minkowski, or something is to, subtract like the infinity from. How you evaluate this without a cutoff, or with a cutoff, so like what you say is still.
Yeah, I would think so. Yeah, there should be some reference stuff.
Thanks.
More questions? Okay, if there are no more questions, let's thank the speaker again. And the next speaker is Andrei Mikhailov. So if you could please share your screen.
Can you hear me well?
I can hear you well.
Can you see the screen with abstract painting?
It looks a bit strange, but yes.
Okay. So the thing, the subject of my talk is related to question. In general, there is general question: what is string theory? What kind of structures we should require. But there is more concrete question: what is string worldsheet theory? String worldsheet theory is a two-dimensional sigma model, but the question is which structures we should require from it. Not any two-dimensional sigma model is a string theory. There are things which should be like big ghost or some additional structures which are required. Energy momentum tensor Brst exact, but what is it really? How to formulate it precisely? What is the actual list and how they approach it? So it seems like I'm going to discuss it from the point of view of BV formalism. So I will consider string worldsheet sigma model as a BV in BV approach, battalion Volkovitsky. So for example, if you consider bosonic string, then the field content of bosonic string are some matter fields or worldsheet coordinates x and complex structure on the worldsheet I, and the Fadeev-Popov ghosts for worldsheet diffeomorphisms. So x, c, and I are fields, and those with stars are anti-fields. So this belongs to a class of BV models which are obtained from Brst formalism. So it is kind of like as classical, which depends only on fields, plus QA phi star A, where QA is some, it's a vector field. So as classical on some fields, but then we add ghosts. And important here is that the master action terminates at the first order in the expansion of master action in anti-fields terminates at the first order. And the gauge group here is the gauge group H. The gauge group H is a group of diffeomorphisms of the string worldsheet. So this is a Fadeev-Popov prescription applied to the group of diffeomorphisms. What is new perhaps in string theory compared to general BV formalism is that it essentially requires integration. There is something less known ingredient here, which is integration over families of Lagrangian submanifold. Usually, to quantize the theory in BV formalism, we restrict on Lagrangian submanifold and then take a path integral. But here, of families of Lagrangian submanifolds. But in string theory, we have to integrate over families, it seems, of Lagrangian submanifolds. So in bosonic string, the choice of Lagrangian submanifold is that we put x star, at least the choice which is usually used is we put x star to 0 and c star to 0. But A runs from 1 to 26. XA. But we put I, the worldsheet complex structure, which is one of the fields in the BV formalism, to some fixed C number tensor, to some fixed tensor on the string worldsheet. And I star is running, so Lagrangian submanifold is parameterized by X, C, and I star. and I star is usually called B. It's a B ghost. So the B ghost of bosonic string is I star. The anti-field to complex structure. But then we have to integrate over the moduli space of complex structures. So we integrate over 3G minus 3, 2 times 3G minus 3 dimensional subspace in the space of complex structures, which covers all the moduli. So this is a procedure which is used. And indeed, always in BV formalism, independently of if you have, if it comes from Brst formalism or more general BV formalism, there is a general procedure of integration over Lagrangian submanifolds. There is a natural measure, and it works in the following way. So given a Lagrangian submanifold L, we consider, suppose that I want to, there are n forms for any n on the space of Lagrangian submanifolds. Suppose that I have n variations of Lagrangian submanifolds, n infinitesimal variations described by gauge fermions, psi1, psi-n. Then I just multiply them and multiply by exponential as usual as BV. So the usually, and this is a form because it's anti-symmetric in one end, and integrate over Lagrangian submanifolds. So in bosonic string, psi would be something like integral mu b plus mu bar b bar, because as I said, B is anti-field to complex structures. So this is what generates the variation of Lagrangian submanifold. But an important ingredient, of course, in string theory, and I argue a crucial ingredient. So this exists in any BV formalism, not only in string theory. In any dimension, it's a very general property of BV formalism. There is a pseudo-differential form on the space of Lagrangian submanifolds. The important crucial ingredient of string theory are Walsh-Sheet diffeomorphisms. So Walsh-Sheet diffeomorphisms should act as canonical transformations on the BV phase space. I propose this as one of the axioms of string theory. So let us look at how it works for bosonic string. Well, so first of all, what it means that so the Walsh-Sheet diffeomorphism should be infinitesimal, should be canonical transformations on BV phase space, which should preserve as BV. So the BV action of the string Walsh-Sheet. And it is therefore natural to assume, and we will require it, that they are exact in the sense that infinitesimal Hamiltonian of Walsh-Sheet diffeomorphisms, or infinitesimal Hamiltonian means BV Hamiltonian corresponding to vector field on the Walsh-Sheet, would be of the form SBV, what Poisson bracket with some function phi, which would linearly depend on vector field on the string Walsh-Sheet. So psi is a vector field on the string Walsh-Sheet. So there must be some function, some way to associate to every vector field on the string Walsh-Sheet some even function phi of psi, so that this BV bracket with BV master action be it should be odd moment map, the PV moment map for diffeomorphism. And of course, they should satisfy that the commutator should be of the same form. So if psi eta is the commutator of two vector fields, then I want this identity to be satisfied. But this, strictly speaking, is not enough, because I want this form to be base with respect to the action of diffeomorphism on the BV phase space. And it is not base, it is invariant form, because this thing manifestly preserves as BV, but it is not a base form, because the substitution, because it's not horizontal. Sorry, please remind me, when should I stop? What is my time limit? 5 minutes, it's 11:35 or it's 11:40?
45.
Ah, okay, nice. Sorry,
sorry, it's 40.
11:45 is my cutoff, right? So the way it works for bosonic string, yeah, so form is the way I wrote it, this definition of the form, which was proposed probably by Albert Schwarz in about 2000. Does not quite work because it's not base with respect. It's invariant but not horizontal with respect to diffeomorphism. So we have to modify it somehow to preserve for it to remain closed, but to be also horizontal with respect to so the contraction of this infinitesimal, this vector fields corresponding to infinitesimal diffeomorphism should be 0. And it turns out that this form has so let me tell you how it works for bosonic string. So bosonic string is example of BV-Brst formalism. So the BV phase space in this case has the form of odd cotangent bundle of the Brst field space. X parameterizes X and I in bosonic string, and H is a group of diffeomorphisms. So this whole thing is parameterized by X, I, and C. It's like a KSZ description of Brst formalism. When we divide by H is a group of diffeomorphisms. When we divide by H, it acts here on the right on H, and there is some action on X. Obviously, diffeomorphisms act on X and on complex structures. But there is a remaining action of H from the left. H can act on itself, every group, by left translations or by right translations. Right translations we used to divide, but there is remaining left translations, and they can be lifted as odd canonical transformations on the BV phase space, and the Hamiltonian, or rather say phi, in this case, phi of psi, would be simply integral over the world sheet of psi alpha C alpha star. So C alpha star is anti-field to the Fadeev-Popov-Gauss, and you can verify that this works. So it is possible to construct base form. I must say that we don't usually discuss it in the bosonic string perturbation theory because we choose family of Lagrangian submanifolds where already this form happens to be base with respect to diffeomorphisms. It's a special feature of bosonic string. In other words, actually what happens is that the corresponding equivariant form would be, let me just copy paste it. It is like this. And it is like this always in Brst BV formalism, actually, but in particular for bosonic string. So I exponentiated this size. I consider it generating functions of all n forms. So it is kind of a homogeneous form of PDF, pseudo-differential form. So expanding in size, we get psi1, psi-n. T are equivariant parameters, so they are technically generators of the Weil algebra of vector fields of sigma. And we should substitute curvature when we go to base form. So to go to base form, we take horizontal projection of psi and substitute this for curvature as usual in equivariant theory. But it's in bosonic string perturbation theory, it doesn't play any role because C star is 0 on our Lagrangian submanifold on the usual choice of Lagrangian submanifold. It is possible to choose other Lagrangian submanifolds where C star is not 0, but I'm not aware of any applications. But if you do this, then in such Lagrangian submanifold, d bar C would not be equal to 0. Sorry, I must say d bar B would not be equal to 0. That's what's important. And then the form will not be invariant under, will not be horizontal. This happens, I believe, in pure spinor. This happens in pure spinor formalism in curved background, but not in bosonic string. Or it would happen in bosonic string if we choose some non-unusual Lagrangian submanifolds. So that's how it works for bosonic string, but for in general, what happens is instead of so in general string theories, there is no C ghost. For example, in pure spinor formalism, there is no C ghost, and therefore there is no C star, of course. So this ansatz is simply special for bosonic string, or any string which is obtained for NSR. It would also work. Any string which is obtained from Brst procedure, where Q is equal to Q Brst. What should we do in general in BV formalism? How we treat the symmetries of BV phase space which we want to gauge out, which we want to gauge? It turns out that there is a slight generalization of this. The form, the string measure, let us call it omega, the string measure, which is constructible in any BV formalism, it has a special property that if we consider V some vector field on the BV phase space, which is canonical, which preserves odd symplectic form, then we can contract it with omega. So omega is closed, first of all, d omega equals 0. But also we can contract any vector field with omega and then take differential. This is usually called, this is usually called a Lie derivative. This is a Lie derivative of omega with respect to V, but for this particular form, it is special. This construction is special. It turns out that exists some differential on the space of vector fields, which depends on omega, so which depends on SBV. And so contraction is very strange. Of course, this is only possible for inhomogeneous forms or pseudo-differential forms. So, and this is essentially the delta, the BV delta, which is, if we represent V as a through a Hamiltonian, BV Hamiltonian, then this d omega will be delta, which is essentially, naively at least, Poisson bracket with SBV. So
5 more minutes. Sorry, 5 more minutes.
Oh.
Yeah, sorry, 10 including questions, but you can take a few more minutes if you need.
I understand, yes. So then in this situation, the following ansatz works. This is for Cartan form. So iota is contraction. So of course, in the BV case, in this case of omega, contraction corresponds to multiplication by, well, it doesn't matter. So in any case, if this is true, then we can use the following ansatz, where I is some possibly nonlinear function of t. And substitution of this ansatz gives us this. So the form will be equivalently closed Cartan form if di plus commutator I with I equals L, where L generates diffeomorphism. So L should be BV Hamiltonian of diffeomorphisms. In practice, this should be all defined together. So there should be consistency conditions that L of Xi Poisson bracket with L of eta should be equal L of Xi eta. So we can consider and that equivariance condition of I of t, but I must stress that L depends on t linearly, while I can depend on t non-linearly. In the special case of bosonic string, I depends on t linearly, and the commutator of I with itself is 0 because C star with C star is 0. It's Darboux coordinates, but in general, and I suspect in pure spinor string. So in pure spinor string, I computed I of t and L of t to the first order in t for pure spinor string in ADS, but I have not computed the commutator. So I don't know if pure spinor string in ADS has higher orders in t. So this equation can be understood as giving a representation in BV phase space or action on BV phase space of some differential graded Lie algebra, which was previously considered in the work of Alexeyev and Severa. And it is called DG construction. It is, in some sense, dual in the sense of Kashul duality to the Weyl algebra. Remember that Weyl algebra is formed by vector potential and field strengths. So this is formed by abstract letters IF. So the way it is usually defined, strictly speaking, it is non-minimal because linearized differential is non-zero. So to make it into a minimal DGLA, I can introduce extra coordinate, extra generator, which I may call Z. It's kind of central. For any Z, this thing is d squares to 0. So let us introduce the central Z. Then with this Z, the DG will be Cauchy dual to this. And it turns out that it has interesting properties. So in some sense, I is it's a generalization of the cone of the Lie algebra, which is the cone of the Lie algebra is generated by Lie derivative and contractions, Lie derivative of size and contractions of size. So L is Lie derivative, but contractions do not have to commute. Alexeyev, in general, this algebras have interesting properties which generalize the property of CG. In particular, there is a map, there is an analog of a map between Weil model and Cartan model, which in the usual, in the case of cone of the Lie algebra, it is given by the contraction. Don't confuse it with this formula here, but it's given by the contraction with T. Sorry, T is equivariant parameter. So if not with T, with theta. What is called A in so the way I reproduced the way I denoted notations, it would be E A iota A for where A is the vector, the letter A, abstract vector potential of the Weil algebra. Then Alexeyev and Severa explained what to do if instead of cone we have this non-commutative analog DG. So not just substitute I, that would be meaningless, but something more complicated. But and this construction has direct meaning in string Paul-Sheet theory. In fact, it can be explained from the point of view of deformation complex, which describes the deformation of the string background. And the physical meaning of Alexeyev and Severa formula is that it describes the procedure of insertion of unintegrated vertex operator. The deformations of SBV correspond to insertions of integrated vertex operator. But we know that in string theory, it is not good to use integrated vertex operators because they suffer divergences due to collisions. So you need to go to something like Feynman-Witten I-epsilon prescription, which requires you to introduce unintegrated vertex operators. And to introduce unintegrated vertex operators, you then have to integrate over the moduli space of insertions. And that's where the generalized Kalkman map is useful. It gives you a way of integrating averaging, the averaging procedure for insertion of an integrated vertex operator, which restores eventually diffeomorphism invariance. So I think we have 3 more minutes for questions, and I will stop here. Thank you for your attention.
Thank you very much. Are there questions? Yes, please, Rita Barta.
Yeah, thank you for the talk. In the terms of the degrees of freedom that you introduced, this XCI variables, what will be the BV bracket? How does the BV bracket look like?
Sorry, I almost did not hear.
So in terms of the variables that you introduced, X, C, and I, what will be the BV bracket? How will the BV bracket look like? Because normally, like you introduce fields and antifields, and you write it in terms of them.
Yeah. X with X star would be delta function, and C with C star delta function. it's just a canonical pairs, I with I star. You have to take care. For example, I is restricted to have I square equals -1. So you have to do some kind of reduction, constraint reduction for I. But it's pretty usual. It's just a PT star or something.
So which canonical vectors do you use? C and I?
So X, C, and I are coordinates like phi, and I just consider odd cotangent bundle to that.
Okay.
Okay, more questions? If not, then let's thank the speaker again. And the next talk is Ivo Sachs will tell us about the field theory of the world line. So please share the slides.
All right, can you hear me?
Yes.
Wonderful. All right, so let me just put this back. Sorry, almost done. So, all right, great. So thank you very much for having me. So I'll talk about not string field theory, but rather some using methods of string field theory to discuss or to scan perhaps some space of ordinary field theories in some sense. So that's one part of my talk. And the other is also at the same time perhaps displaying or highlighting some background independent structures, which should also be there in string field theory. So that's somehow the motivation of this talk. So in that sense, perhaps fits in this tomorrow's discussion of sort of beyond string field theory or below. So first I'll give some general construction. This goes into this framework of the underlying idea of this project, and then I'll finish with some examples. So that's the idea. So I should warn you though that the examples, so the explicit results are rather, I would say, modest in the sense that it doesn't go very far in terms of explicit examples, but we'll see as we go along. So be warned. All right. So for the motivation, so that comes sort of a string field theory motivation, perhaps. So if you had some BV field theory, so you had some space of fields, and you had some BV operator, perhaps, and some BV action. So that would be a truly background independent formulation of some BV field theory. Now, once you have such a BV field theory, you can always associate homological vector field to it. So some nilpotent vector field. That is simply, for instance, if you have an action, you could just take this thing. That would be some vector field. And then you can expand this vector field around some critical points. Say you take in string theory, you could think of taking Minkowski metric and no other fields sort of switched on. That would be some critical point. And then you can expand around the critical point, this homological vector field, and that gives you some expansion coefficients, which are denoted by QK, which then automatically satisfy the axioms of some infinity algebra or the vertices of some string field theory. So that's really where string field theory lives. So you take some critical point and you expand around that critical point, and you perturbatively build an action in terms of these QKs, which would be the vertices. So then of course you can go on and compute Feynman diagrams with this string field theory, and you will recover what we call the perturbative string theory or the worldsheet formulation. So that would be over here. So now one might want to go the other way around. So one might want to, that's sort of the aim of this project here, is to try to go somewhere here. So that would be some notion of background independence. So you reconstruct somehow the action where all this structure came from. So that's somehow, perhaps you don't quite need to go there. You might also say it's perhaps enough to reconstruct some homological vector field, in which case you wouldn't have an action, but at least you would get some equations of motion, as that would be as the critical points of it. So, but we'll see. So and that's really what I'm trying to do here. So what I'm going to do is, the idea is that what we do is from string theory, we can go here, perturbative formulation of string theory, extract some algebra, some graded algebra, which is going to be the algebra of the BRST quantization. So let me say algebra A. And then once you have this graded algebra, there's a kind of canonical construction to construct such a homological vector field. So that is a canonical construction. So that's going to be the first part of the talk, how say for Q. And then once you have done that, then you might ask, so what have I done? What field theory did I obtain? So what, then the question would be then, what field theory do I get in this way? Theory do I get? So that is really the whole talk about. So that's what I'm trying to do. All right, so then let me first discuss a little bit this construction of this Q. Let me go on to the next slide. So you have this picture again. See a bit better. So as I said, concretely in string theory, we know we have, when we BRST quantize the worldsheet, we get a set of operators, which is momentum. We have the embedding coordinate. We have the B goes, C goes, beta goes, gamma goes, and possibly other fields. So that naturally provides us with some graded Lie algebra. So that is what I was advertising there. So the algebra is given to us. And now I want to construct a homological vector field just based on such an algebra. So for a given algebra, there is this way of constructing a homological vector field. And it's really well known actually from the Chevalier-Eidenberg complex. And what you do is simply, you take an element, and you take this graded Lie algebra, and you're looking for an element of degree 1. So say goes degree 1. And you expand this element in goes degree 1 in a basis. So let EA be a basis in this graded Lie algebra. And then you simply expand omega in terms of some coefficients, which themselves not need to have an appropriate grading in order to get total grading, goes grading 1. So that is something one can do. And then we can define the homological vector field Q simply by taking the graded commutator of omega with itself. So that's a linear field, of course, in terms of it's linear in size, and then you can extend it to higher order functions by using the Leibniz rule. So that's sort of this canonical way of doing this. So let us ask then, so what did we achieve? So perhaps we go to the next slide. So if this is, say, this supposed to be space of fields, which we perhaps don't know in string theory what it is globally, but we do know, say, in the neighborhood of some point, what the space of fields is. So say omega 0 could describe, say, as I was saying, perhaps a Minkowski background with no other background field switched on. So that could be a particular point in the space of field. And then here we do know how to do, say, conformal field theory of the Polyakov action. So here we have a string theory construction. And this provides us, as I said, with some graded Lie algebra just through the BRST construction, which we can do at this point. Now, what I'm going to assume is that this graded, if I had done somewhere else a similar construction, although I perhaps don't know how to do, I perhaps could still use the same algebra. And then this construction which I just described, so let me go back perhaps one slide just to show it again. So now we've extracted the algebra, and from this algebra we now construct this homological vector field. So now we construct a field, maybe like this. So this is my homological vector field, which is defined naturally in some part of this space of fields where this graded Lie algebra doesn't change. So I denote this perhaps by D of A. So here I'm assuming that the algebra is the same in that region of field space. That may not be the case globally. I mean, in string theory, surely there are configurations where we do not have a worldsheet description of it. I mean, there must be in fields, in string field theory, there will be such configurations. So then this BRST algebra might be quite different. So there's no reason to assume that this would be a global construction. But locally, we can try to do that. So then we've extended this homological vector field, and then we can say, well, let's perhaps look for critical points of this homological vector field. So perhaps there might be some other points here, which are denoted by omega bar, which will be critical points of this homological vector field. So I've written that down here. Suppose some Q bar, which I took to be Q of omega bar, is omega graded commutative with omega bar, and the sum is equal to 0. So then we are back. So then let me perhaps go back in the slides two more. That means I have a critical point, and then I can expand around the critical point, and I will do another perturbative theory around that point with naturally some string vertices which satisfy all the necessary conditions. So that's really the idea. You extract the algebra, and based on the algebra, you construct some homological vector fields, and afterwards you can look for critical points. So once you've found such a critical point, there's naturally a gauge symmetry associated to it, because if you take omega bar and then you do some graded commutator with some degree 0 object in the Lie algebra, you get another solution. So automatically, once you find an omega bar, so a solution, a Maurer-Cartan element, you will have some gauge theory associated. So perhaps what I'd like to emphasize here is that so far this construction is background independent, so long we were justified basing our construction on this algebra which we were given at the given point. Other than that, I have not assumed any background data. So now I could, in principle, if I find another critical point, I can then expand around this critical point and build another perturbative. I can build another action if I want to. So that's the idea. Now, as I said, so then you might ask, well, suppose we've done that, what kind of gauge theory do I get? What am I describing here with this procedure? And surely that would depend on what graded algebra you started with. So let me perhaps go to the next slide. So that's the question. So what I'm going to do is I'm going to take my element in the algebra, of course, degree 1, and I consider this as a generating function of space-time fields. So how can I do that? So I had already said I can, any element of omega of degree 1, I can expand in terms of the basis of the Lie algebra with some coefficients graded. But what I can do is I can, since x mu, remember x is part of the algebra, so is p. So, but what I can do is I can absorb the x dependence in some wave function. So that would be some wave function. And then this is again a basis, but now independent of x. So I just split the base of the algebra, so I sort of take out the x dependence. I put the x dependence into these coefficients, and then these will be graded fields. So these will be the space-time fields associated to a given algebra. And this, of course, the full BV spectrum will automatically be there. All right. So then I want to impose that this omega is a Maurer-Cartan element. So I should satisfy that the Q of omega is equal to 0. And then this will imply some equations of motion for these space-time fields. So that is the recipe for describing the field theory which you get in such an approach. Of course, it's still very general. Are there any interesting examples? Is to be seen, but that's the idea behind it. So again, I should say that here I have no action, so I'm just looking for equations of motion. So it's not guaranteed at all that any of these systems which I get will derive from some action, but maybe that is not necessarily needed for a classical field theory. And another comment perhaps which would be worth making is that at this point, I have not assumed any representation of this algebra, of this BRST algebra on some space, on some state space. So I have not introduced a photon or a gluon or anything. It's just a purely algebraic question so far. Okay, so that's the general structure. So whenever you give me an algebra, there is a graded algebra, there's always a way to construct a field theory out of it. That part is in a way easy. The difficult part is to identify an algebra that gives you an interesting field theory. And that's what I want to describe now. So that I would call this part of examples. All right. So now, in order to get, of course, you give me a generic algebra, probably is going to lead to nothing interesting. So that's where I make some educated guess. And of course, what I do is I take some models which I already know, and I try to sort of extend these models or see what they contain. So now we know already that the spinning word line, so word line so relativistic particle with word line supersymmetry gives a BRST algebra. And it's of course much simpler than the string because it doesn't have all these higher oscillator modes, it only has one oscillator. Okay, and it's already known for a long time, in fact, that for instance, if you take the spinning particle with n equal to word line supersymmetry, there is a way to describe a Yang-Mills theory. This way, that was the BV formulation, Bartolini-Lukavidsky formulation of Yang-Mills theory, 3-level. In this way, in 2008, there was a paper by Siegel. Should say, however, there was already much before field theories have been obtained from the point particle of the pure spinor formalism. So there's another way of doing it, and that would historically preceded this by a lot. It was Knighton's work. You could also get from this n equal 2 word line, you can get, actually you have to do some extension, you have to add a few extra generators, but then you can get the Broca field, so massive fields. So we know in principle there's a way to obtain realistic field theories from this kind of algebras. Now, the purpose of this work will be to sort of classify them, so to scan the space, not to pick one example, but to see what can you get a given algebra. For n equal 4, there's a similar story. For n equal 4, you can get Einstein action, or not action, equation of motion for the Einstein theory, or also for the whole massless sector of the Bosonic part of string theory. So in the same way. Again, there is a pure spinor version of this. So this was sort of motivation of where to start. So that gives you a starting point. So that seems to say perhaps that's a good start of an algebra. So basically in the rest of the talk, I'm mostly going to focus on the algebra that arises from the word line of the spinning particle with n equal 2 word line supersymmetry. So that is what I have here. Let me perhaps make more space. So the algebra then is given by, as we had, the x, the p, the theta mu, and the theta bar mu are the word line spinners, but as space-time vectors. And since they have n equal 2, I have 2 of them, and then usually I have the BC ghost, the gamma gamma bar, beta beta. You know this very well from string theory. So these are the kind of the zero modes which you would have in string theory, just simpler. All right. So now suppose let's write down the most general element of degree 1, ghost degree 1, which expanding in the basis of these fields or these generators which you have in this algebra. And then you impose this Maurer-Cartan condition and you ask yourself, what do you get? What's left? And what you find is this, maybe I put here a gamma bar just to say that would be a solution. And what you find is actually not too much interesting in a way. There turns out to be one scalar which can survive, which turns out to be identified with the dilaton later on. And then there can be a metric background, which is unconstrained, no conditions at all, apart from this has to be torsion free. And then you can get higher spin backgrounds, which are also unconstrained. So then you might say, okay, it's something, but it's not quite what we want. Okay, so we'll see. So in particular, you don't get Yang-Mills theory like we had on the last slide, doesn't seem to be there. Gravity seems to be there, but is off shell. So not quite what we want. You could repeat this exercise with n equal 4, and you'll find that, again, you'll find that there's no vector field. There is no, in fact, the metric is set to Minkowski metric. The dilaton is also set to 0. So there's nothing left. So it seems nothing interesting. Now, so that something has gone wrong. So the conditions were too strong. So the conditions for nilpotency just was too strong to have anything interesting left. Now, so in order to proceed, I want to do two things. I first want to disentangle all these fields of higher spin. So here I have all these higher spin fields, which seem to be off shell. So somehow I would like to keep them a little bit apart. I can do this by introducing a suitable filtration. I'll tell that in a second. And the second thing we want to do is we want to reduce the algebra. So since the algebra is too big. Okay, so let me describe that in the next slide. Yeah. So as I said, first I'm going to introduce a filtration, which is basically the dimension. So we know that the momentum operator has dimension 1, the x has dimension 0, the c goes has dimension -1, and so on. So basically you filtrate your vectors, your algebra in terms of these dimensions. And that's basically this filtration here is just a dimension. So that just means you can gives you a way to organize the fields a little better.
5 minutes.
Yep. And so just to mention, perhaps here you will get, for instance, in filtration 0, there would be a vector potential, filtration 1 would be metric and so on. Second thing you want to do is you want to reduce the algebra. So you reduce the algebra. Now we introduce a representation space. Suppose you have some module, and you consider some submodule, which is so in H, and you want your elements in the algebra to preserve that submodule. So you don't want to generate states of arbitrary high excitation, for instance. So that gives you an algebra. Then what you do is you divide, you identify elements in the algebra which actually annihilates, which act trivially on the subspace. So that's this ideal, and that's it. So then that is a new algebra. So this is a consistent truncation. That actually depends now on what you do for H, what you choose for your submodule. We will fix the number of thetas in the Fock space, the gammas, the betas. We fix it equal to 1. So that kind of means sort of BV version of, say, you only can have one photon state or a photon state, basically. Okay, now in this filtration, let's now go to filtration 0 in the reduced algebra, A prime, and let's write down the most generic extension of the BRST or the omega degree 1 object that you can write down. It does not necessarily need to come from a field theory. You just write down whatever you can write down in the filtration. And then you ask again, what does it mean that, that Q of omega equal to 0? So what does it give you? And that, let me show you on the next slide. What it gives you is this. So it sets, for instance, this field is set to 0. It turns out that this auxiliary field is expressed in terms of some vector potential and some scalar. Here the same thing. You get lots of conditions. And in the end, what's left is a vector potential and a scalar. And you get, for the vector potential, you can define a field strength. And the field strength has to satisfy Maxwell's equation if this scalar is set to 0. So this is again the dilaton. So in this theory now, you get, in fact, an off-shell dilaton and a Maxwell theory, which is almost Maxwell up to this extra term. So this is a complete classification of the n equal 2 word line at filtration 0. There is a non-abelian generalization of it by extending the filtration to the Lie algebra, the universal enveloping algebra of the Lie algebra. And maybe just as a comment, if you extended this analysis to n equal 4, this dilaton would go on shell. It would be expressed in terms of the metric, which is itself also constraint, but then there's no vector potential, just as to see how things work a little bit. But we don't have a complete, this is not complete. We don't have a complete classification of the n equal 4 word line. We have for n equal 2 in filtration 0. So this is just, as I said, the results are modest, and that's the kind of modest result. You say that's the algebra. What's the most general field theory which you can get, and there it is. Okay, so maybe just almost done. So what is the interpretation of this A prime? I think there's a physical interpretation which is sort of quite clear, is that by reducing to this submodule, and we wanted the submodule to be preserved, what that means is that we only want, for instance, in a gravity background, only the graviton needs to be defined. I don't expect any higher states, higher massive states to be well defined in a gauge invariant matter. Or say, so that's the submodule. So I think that's the same as in string theory. If I solve the low energy equations of motion in string theory, I cannot assume that a higher spin state can propagate consistently on this background. That would be too much. So that's what this A prime means. So it has a simple physical interpretation. So now, so this was the story. Now, one may ask the question, does this theory which you obtain in such a way, does it derive from an action? Now, if you had a non-degenerate invariant trace on this algebra, you need to be of degree -3 because this has degree 1. Then automatically you could write down an action. Then simply you take the action to be trace of omega with omega squared, and then this would be gauge invariant by the invariant trace. And it would, if it's non-degenerate, it will also automatically give you this condition, which was omega of q of omega. Sorry. So if you had a trace, then you'd be done. You can automatically always write down an action. However, you see, there is of course always a trace. There's always the killing form, but we need something in degree -3. And that turns out to be much harder to construct. And in fact, we weren't able to construct such a trace, which is invariant. We were only able to construct such a trace, which is invariant if, say, how to say, let me write this quickly. So we need something like, okay, let me not waste time, but which is only invariant in some subset of fields. And that is enough to construct quadratic actions, but is not enough to construct, for instance, the nonlinear action of Yang-Mills theory, which we know is in this theory, but we cannot get an action for it. You might say, well, perhaps there's another way of doing it. You use an operator state correspondence, you define wave functions, and then you use, again, what we know from string theory, you try to write an action like this. But unfortunately, here doesn't work because omega 0, so the one without any background fields, that turns out to be not a derivation of this natural product here. Since it's not a derivation, you don't have gauge invariance. That is, again, in contrast to what you have in string theory, where you have the star product, for which this is a derivation, of course. Or also in the pure spinor construction, where omega 0 is a linear operator in the momentum, and in fact, the normal product of functions is omega 0 derivation for it. So we are not able to actually produce an action in general case. So that's sort of a disappointment. Okay, so let me just conclude. So what would be nice to do, maybe to extend this classification to higher, bigger algebras, and perhaps find new field theories that we hadn't anticipated before. So that would, so natural place to go would be n=4. N bigger form might also be interesting because it should give higher spin theories if they are consistent, but I don't know whether that's going to work. Another thing which might be worthwhile would be looking at Ramadan fields. We have some ideas, but seems like one needs to go into this pure spinor way down for this. And also a thing that might be quite possible to do is an extension of this classification to the ambitwister string, because the ambitwister string is very close to the point particle in the sense that many things can be done. The PRST charge can be defined off shell. So it's that is probably doable. All right, and I think I should stop there. Thank you.
Thank you. Okay, are there any questions? So, Alex, please.
Hello, can you hear me?
Yeah, just about.
Ah, just about. Okay, I'll make myself louder somehow. Okay, this should be better.
Yeah, now it's good.
Okay, well, thanks, Ivo, for the very interesting talk. I was wondering about the first part of your talk on background independence from the graded Lie algebra.
Mm-hmm.
So the starting point is it's a DGLA, it's a differential graded Lie algebra, right? And
right.
Then you.
Well, it doesn't necessarily need to have a differential. Just needs to have just needs to be a graded Lie algebra. You don't need to have a differential.
Right. Okay. Even better.
Actually,
so,
typically I won't have.
I'm happy with that. But so my question is the following. So we know that in general, if you have some field theory or string field theory even, and you go to the homotopy algebra formulation, you calculate the scattering amplitudes, and you get a minimal homotopy algebra. And if it's closed strings, for example, you started with an L infinity algebra, you end up with a minimal L infinity algebra, and outcomes which contains as a subalgebra a graded Lie algebra, in fact, but it also contains a bunch of higher brackets which correspond to more than 3 states entering in a string scattering amplitude. So, and if you have that information, so the minimal L infinity algebra, you can follow, the mathematician's footsteps, introduce twistings by Maurer-Cartan elements, and follow through the steps in this background independence argument. But that algebra is not just a Lie algebra, it also has a higher bracket. So my question is, are you specializing to cases where the minimal model is a Lie algebra in this, or is this a genuinely different kind of algebra?
So the moment you expand around a given background, you will always generate higher brackets, which will just automatically be L infinity because of Q squared, omega Q squared equals 0, so that's guaranteed. And of course, if you expand around if you take here, you can expand around some omega bar. So this defines a perturbative differential, and then you can go in the cohomology of this differential and then get the minimal L infinity algebra there, which will be just the S matrices, of course. Yeah. So that all that goes the same way.
Right, but the thing you're actually using, that's not the Lie algebra come from minimal model, or is you're using a strict model?
No, I'm actually, the algebra I'm starting is just the BRST algebra of quantizing the word line, or the word sheet if you were in the string. So there's no structure there other than being a graded Lie algebra. That's all.
I see. Okay, but for the string case, you haven't passed to the cohomology. It's off shell.
No, it's completely off shell. Yeah.
Okay. I think that clears it up for me. Thanks.
You're welcome.
More questions? Okay, if there are no further questions, let's thank Ivo again and go to a 13 minutes break.
You're welcome.
Oh, I'm sorry.
The next talk will be given by Ted Erler, who will tell us about homotopy intertwining solution. Ted?
Okay, thank you to the organizers for inviting me to give a talk, and thank you everyone for showing up and listening. So, okay, so the title of my talk is Homotopy Intertwining Solution. Okay, so in these 2 papers, Carlo Macaferi and I developed what was called intertwining solution, which purports to demonstrate the non-perturbative background independence of Witten's open bosonic string field theory. So what this means is, first of all, that Witten's theory on some reference D-brane includes classical solutions which represent all other D-branes in that closed string background. And secondly, what that means is that if you have 2 Witten theories which are formulated on 2 different D-branes, then these theories are related by a field transformation, which is invertible up to field redefinition. So, so in this talk, I'd like to describe a an extension of this solution, which can apply to string field theories whose gauge invariance is based on a more general homotopy algebraic structure. Okay, so the idea is to get some deeper understanding of the structure and maybe suggest some new solutions. But in most situations, it will not really be realistic to expect that this solution can be realized in a fully explicit way. So, but there are some circumstances where it can be, and we can put some of these ideas to the test. So what I think is perhaps most interesting is the idea that this kind of framework for a solution could tell us something about classical solutions in closed string field theories. So to really entertain this idea, we have to believe that closed string field theory supports a tachyon vacuum solution, by which I mean something very specific, that there is a classical solution in the theory whose kinetic operator does not support any cohomology. Okay, but other than this assumption, I've tried to be mindful of anything in the construction which might distinguish between open and closed strings. So, okay, this being said, I will present all of the equations basically in the language of A-infinity algebras and the tensor algebra rather than L-infinity algebras and a symmetrized tensor algebra. This is just because I find the notation a little bit more comfortable, but everything that I write has a corresponding symmetrized expression. So, so first, let me tell you a little bit about this intertwining solution as it's been understood up to now. So the idea is that we have two string field theories, one string field theory on some reference D-brane, and another string field theory which is defined on some target D-brane. So these string field theories are to be related through a classical solution, which we call the intertwining solution. So the intertwining solution takes this form. So the first term is the tachyon vacuum solution on the reference D-brane. And the second term in here is the tachyon vacuum solution of the target D-brane. Okay. And so we're somehow subtracting one tachyon vacuum from another. But this sigma and sigma bar are called intertwining fields. And what they do is they allow us to, this tachyon vacuum on the target D-brane, okay, lives in a different vector space from the one from the reference D-brane. So these intertwining fields somehow allow us to give a dictionary which allows us to express this tachyon vacuum solution in the variables of the reference D-brane. So, okay, that's the structure. So this solution satisfies the equations of motion under two assumptions. The first assumption, which I will call the invariance constraint, is that these intertwining fields, sigma and sigma bar, are invariant under the action of the kinetic operator around the tachyon vacuum. And the second condition, we'll call the non-degeneracy constraint, which is that the sigma and sigma bar and sigma, when multiplied in this order, give 1, by which I mean the identity of Witten's open string star algebra. So now we would like to see how this structure could be generalized. So we start kind of in a very general way by considering a string field theory of a reference background, having some dynamical field psi ref, which lives in the reference vector space, and some string field theory defined on a target background, given by a field psi target, which lives in the target vector space, okay? So we have these two string field theories, and they're defined by cyclic A-infinity algebras. So there's a cyclic A-infinity algebra for the reference D-brane, given by these products, and the cyclic A-infinity algebra for the target D-brane described by these products, okay? And the statement that these form cyclic A-infinity algebra can be expressed in the language of coalgebras by saying that these products form a coderivation which squares to 0 and satisfies this compatibility condition with respect to the symplectic structure defined on the vector space. So this is the statement of cyclicity. So on these string products, I have an index PV, which stands for perturbative vacuum. So that indicates that these are the cyclic A-infinity structures that are obtained from expanding the theory around the trivial solution, the perturbative vacuum, where both the reference and target string fields vanish, okay? And our third assumption is that we have that both the string field theories on the reference background and the target background have tachyon vacuum solutions, psi TV, okay? So a comment about notation is that these cyclic A-infinity structures on the reference background and the target background don't have to be the same. And these tachyon vacuum solutions also don't have to be the same when expressed in some universal basis. But I will not, my notation does not distinguish them because for the most part, the distinction is not important. And when it is important, it should be clear which structure I'm talking about based on what vector spaces things live in. Okay, so now if we expand these theories around the tachyon vacuum, we can expand the reference theory around the tachyon vacuum and the target theory around the tachyon vacuum. We obtain two other cyclic A-infinity structures given by these string products, okay? Where now the index TV means tachyon vacuum. So this is the A-infinity structure around the tachyon vacuum. So the A-infinity structures of the tachyon vacuum and the perturbative vacuum are related by an A-infinity morphism, okay, described by some cohomomorphism S, which is called the shift, and we have this simple relation, okay. So the key assumption in what follows and a defining feature of the tachyon vacuum is that the kinetic operator around the tachyon vacuum does not support cohomology. Okay, so this is the setup that we're considering. So now we would like to find some kind of generalization of this intertwining solution. So I propose that we write something like this. Okay, so we have the intertwining solution, which we're going to write like in this form. And this I1, I2, and I3, okay, these are string products, which I will call intertwining products. This I1 is something analogous to the sigma bar psi tachyon vacuum, sigma psi tachyon vacuum, sigma bar that we found in the original intertwining solution. So these intertwining products are just maps from the target vector space. They're multilinear maps from the target vector space into the reference vector space. So I1 just takes a target string field and maps it into a reference string field. I2 takes a pair of target string fields and maps it into a reference string field, and so on. So in the context of the open string, we can imagine this, this intertwining product as basically, roughly speaking, just a pair of boundary condition changing operators which have been put on either side of our state in the target theory, okay? These boundary condition changing operators relate the boundary condition of the target theory to the boundary condition of the reference theory. So in the closed strings case, okay, if this applies, it would seem that this would have to be some kind of a defect operator, which somehow forms an interface between a bulk target CFT and a bulk reference CFT. Okay, so the intertwining products that we've introduced naturally define the products of a cohomomorphism, an A-infinity morphism, which I just write ITV. And in terms of this, the solution can be written like this, as in terms of the A-infinity morphism, okay? And we can also define intertwining products around the perturbative vacuum using this shift. And then the solution can be written even more simply by acting this cohomomorphism on the identity element of the tensor algebra of the target background. So now we want to see how this will solve the equations of motion. So the equations of motion of the reference string field theory is just that the A-infinity structure around the perturbative vacuum should annihilate the intertwining solution, basically. So, so this follows in a very natural way if we can assume that the intertwining products define a morphism between the A-infinity structures of the reference and target background. So basically, if the A-infinity structure, so basically if this cohomomorphism I commutes with the coderivation defining the string products, okay? So, so this follows naturally because then essentially this equations of motion for the intertwining solution will transfer through the intertwining products into the equations of motion of the tachyon vacuum of the target theory. So this generalizes the invariance constraint that I wrote earlier for the intertwining fields sigma and sigma bar in the original intertwining solution. Okay, so so if we expand this this relation in terms of constituent string products, we find an infinite hierarchy of relations which these intertwining products must satisfy. So in particular, the first intertwining product must be invariant under the action of the kinetic operator around the tachyon vacuum. And then the higher intertwining products, there's more complicated relations. But the essential observation is that the right-hand side of these equations is automatically killed by the kinetic operator around the tachyon vacuum. And since QTV has no cohomology, this guarantees that we will be able to solve these equations to find the intertwining products. So, okay, so we could solve the first relation by just, so for the first intertwining product by just postulating that it's a commutator of the tachyon vacuum kinetic operator with some other operator here, where I1 bare is basically any pair of boundary condition changing operators or defect operator that relates our backgrounds. And it can be chosen based on what we're interested in and what is convenient for us. And to solve the second equation, this one, we postulate that the two-string product around the tachyon vacuum can be written in exact form relative to the kinetic operator around the tachyon vacuum, where this U2 is a two-string product, which we call the gauge 2 product. Okay, and if you construct such a U2, then the second intertwining product can be written like this. And similarly, if you introduce a gauge 3 product satisfying this relation, where MTD3 is the 3 product around the tachyon vacuum, then you can find the intertwining 3 product, with a more complicated equation like this. So the general story has some parallel with homotopy algebraic constructions of superstring field theories. So the idea is that you have a hierarchy of gauge products, which I'm calling UN, where n is greater than 2, which can be assembled into a coderivation which depends on some parameter t, like this, okay? With this coderivation u of t, we can form a cohomomorphism defined as a path-ordered exponential, like this. And then these products, U2, U3, and that should be a U4, are determined so as to satisfy this relation that the A infinity structure around the tachyon vacuum is U inverse QU, where Q is the kinetic operator around the tachyon vacuum. So this U relates the A infinity structure of the tachyon vacuum to the trivial A infinity structure just defined by the kinetic operator around the tachyon vacuum. Okay, with this, the intertwining products in our solution can be written in this way in terms of U inverse and U, and our first intertwining product, which we are essentially free to choose. Okay, and then the intertwining products around the perturbative vacuum can also be written by just incorporating this shift. Okay. So now some comments. Okay, so the first comment is that, okay, our infinity notation aside, there's nothing in what we've done so far that really distinguishes between open and closed strings in an essential way, except perhaps about the existence of the tachyon vacuum. The second comment is that this cohomomorphism U that we've constructed out of these gauge products must be singular when it acts on any physically interesting field configuration. So to see why this is the case, we consider the field redefinition psi prime U acting on this thing, where this is our original string field psi, okay? So this field redefinition will map the equations of motion around the perturbative vacuum, which we know are physically interesting and non-trivial, to this linearized equation of motion around the tachyon vacuum. So this second equation has no interesting solutions. So that means that something about this field redefinition is not allowed. And so this operator, this cohomomorphism U, must be singular. But we see that our intertwining solution was really made out of this operator U, okay? So, but it may nevertheless happen that that the solution is well defined, even if the operator U is not well defined. So this is similar to how we can write the A infinity structure around the tachyon vacuum using this equation. So even though U is singular, we can still write such an equation. It's well defined. Okay, but this means that okay, the regularity of this intertwining solution is a non-trivial matter. Okay. The third comment is that so far in our construction, we have not utilized anything analogous to our non-degeneracy constraint, sigma bar sigma equals 1. Okay. So this is good because this constraint in our original solution is really the main source of difficulty with realizing it. Okay. In the first version of this solution, which I published with Carlo, it requires tensoring with this, it requires restricting to time-independent backgrounds and tensoring with an unphysical time-like Wilson line, and it leads to associativity anomalies. In a more recent iteration of this solution, it requires working with complicated and singular surfaces and also the perturbative vacuum is represented by a non-perturbative state, which is kind of weird. Okay, but if we don't have this non-degeneracy constraint, okay, we need to deal with a solution which contains an unbounded number of boundary condition changing operators, or defect operators. And we have to confront the question of convergence. And at a practical level, explicit computations become more difficult. So, so what time is it now? Okay, so I probably have 5 minutes.
5 more minutes, yeah.
Yes, so, okay. So I wanted to give some examples. So first is kind of the trivial example is the original intertwining solution itself, how it fits into this framework. So the intertwining products in this case are just trivial. You only have one product and all the higher products vanish. So the gauge products, which go into this construction, are also important, even though they don't appear explicitly here. And the correct choice turns out to be this, that the product of x and y is given by minus xay, where A is the so-called homotopy operator, okay, around the tachyon vacuum solution that satisfies QTVA equals 1. And with this choice of U2, it turns out the higher U's can be chosen to vanish, okay? So, okay, so with this choice of gauge product, turns out that the reason why we can choose these higher intertwining products to vanish is because this intertwining product commutes through U2, and this is basically follows from the non-degeneracy constraint. So now I think I have to hurry up. So I wanted to give more examples, including some non-trivial ones, less trivial ones, but I think that so now I would like to get to background independence. Okay. So we have this kind of formal algebraic construction of a solution, which is supposed to represent the target background from the point of view of a reference background. So the most important way we can know that we've succeeded is to somehow use this solution to map the action of the reference background into the action of the target background. And in this way, we will have established background independence. So in the context of our solution, this homotopy intertwining solution, the most natural field transformation we can consider is basically just defined by these intertwining products, in this case, just written around the perturbative vacuum. So this should be our field transformation. And we just plug this transformation into the action of our reference background and see if we can reproduce the action of the target background. And this way we know that we've succeeded. So here I encountered some problems. Okay, so at least at first, since I was, okay, there are a lot of defect operators or boundary condition changing operators which are flying around when you plug this into the action. And so I tried to get some intuition by looking at what happens with analogous solutions in the Witten theory. And here I found that it was essential in these computations that these two pictures, okay, here are the same. So that if you have a state in the reference, if you have, okay, an inner product of two states in the target background, which are separated by boundary condition changing operators, these can somehow be written like this, that these lines here, okay, don't matter. So for the open string, this is obvious because there's no difference between the bulk CFTs of the reference background and the target background. So the fact that we need an assumption like this to prove background independence is kind of worrying. Okay, so for the closed string, if these lines represent defect operators, we would not expect such a relation to be true. Okay, but okay, I was still able to make progress by assuming that the gauge products in our construction are cyclic. Okay, so this seems like a natural condition. Okay, but it's not realized in the known intertwining solutions that I have worked with so far. But nevertheless, we can take this to be true. And if you do that, then you find that all of these defect operators and boundary condition changing operators in the action can be canceled down to just two, okay, which appear in the action like this, in a BPZ conjugate pair. And then you just postulate that this object, which appears in the action, can be written as the identity operator minus something which is trivial around the tachyon vacuum with respect to the tachyon vacuum kinetic operator. So this identity operator gives you the action of the target background just as you need. And this contribution gives some terms which vanish on shell. So in this way, it seems that we are able to at least algebraically prove background independence without really assuming anything about whether we are talking about open or closed strings. Okay, and the final point is the question of the convergence of this solution. Okay, and another point is this non-degeneracy constraint of our of sigma and sigma bar. Okay, so I think these issues are related. Okay, so in fact, if you are able to realize this non-degeneracy constraint between sigma bar and sigma, then you are guaranteed convergence since the solution only has two terms. So the non-degeneracy constraint is essentially saying that these intertwining products transfer all information about the target background into the reference background. So if they do not, it's hard to believe that this computation that I did, which showed the equivalences of the actions, could really be valid. Okay, so so this leads to the conjecture that this homotopy intertwining solution will faithfully represent the target background only if this bilinear form of this defect or this operator here, if this bilinear form of this operator which we use to construct the solution is non-degenerate. Okay. So if this applies to closed strings, the implication is that two bulk CFTs can be dynamically related, okay, in closed string field theory and presumably in string theory, only if there is a defect operator such that the bilinear form written here is non-degenerate, okay, where A is a state in your reference on your reference background and B is a state on your target background. So it would be interesting to see if this leads to a reasonable picture of the string landscape. Okay, so that's all.
Thank you. Are there any questions? Ivo, please.
Please switch on. Hi, Ted.
Hello.
Very nice. I had a question about, you know, when you defined this U, you had this path-ordered integral from 0 to 1.
Yes.
And could that be made continuous? I mean, could you replace 1 by any parameter and then continuously interpolate between 0 and 1, or it doesn't work?
Oh, yes, you can replace it with any parameter.
So it would be kind of
that's
continuous.
what we do on our paper, yes.
I mean, that's interesting, no? Because it means typically two different backgrounds may not be related by a continuous transformation, but in this case it would be, I suppose.
Well, okay, so if you have some intermediate T, then you don't fully have the A infinity structure of your
I see.
background. Okay, you have an A infinity structure with a redefined coupling constant, you could say.
Oh, so it's representing the coupling. Okay. Yeah, thank you.
Hello?
Okay, Yuji, please.
Hi. So I'm not sure. I didn't follow all the notation, but if I remember correctly, your solution is constructed from I1 something, I1 bear, or I1 something, and U, right?
Yes. So there's I1 bear, which is basically our defect or pair of boundary condition changing operators, which we could choose at our will. And then we basically multiplied by an operator of ghost number -1, take Q tachyon vacuum of that. And then we have some I1 tachyon vacuum. And this is the analogy of the sigma bar psi, or sorry, sigma psi sigma bar that appears in the original solution.
And okay, so my question is, are there any constraints on the U, U2, U3, etc.?
Well, the constraint is that they should, okay, at first the constraint is simply that they should allow you to write the A infinity structure around the tachyon vacuum in Q tachyon vacuum exact form. Okay, so that doesn't determine them uniquely, but you will always be able to find a solution for these U's because Q tachyon vacuum has no cohomology.
I see. So there are actually many ambiguities, but then the solution is guaranteed to exist, right?
Yes.
Okay.
So it's guaranteed, well, perturbatively, it's guaranteed to exist somehow, but whether it sums into something that is really meaningful is kind of the non-trivial question.
Okay. Thank you.
Michael?
Yeah, okay. Martin, please.
Can I ask a question? Hi,
Sure.
Ted. A very nice talk. So my question is, have you examined the properties of the D operator? Do you really need the fact that it's a conformal defect, or you need a stronger condition that is B topological defect, or you need weaker condition? And where these conditions come from?
You know that it cannot be a factorizing defect. That's all I know for sure.
Why it cannot be a factorizing?
Because then this bilinear form that I wrote at the end of the talk will be degenerate.
Okay.
So this is actually kind of an important point, which is that this condition that I wrote at the end of the talk seems to be potentially non-trivial. So it may imply some condition, it may have some implications as to what the space of closed string vacua really are. So it's not obvious that given two completely arbitrary bulk CFTs, you would be able to find such a defect where that bilinear form will be non-degenerate. Okay, and I'm kind of hoping that such a condition might give us some idea as to what really background independence should be for the closed string. But this is kind of speculative.
Mm-hmm. But this non-degeneracy condition is more like a technical condition, or?
Technical. I'm not sure what you mean by technical.
So
I mean,
would something go fundamentally wrong if this was degenerate? Or?
Well, if this thing is degenerate, then basically you know that the information about your target background is being destroyed on its way to the reference background. Okay, so you know that basically if you try to relate these two backgrounds through such a defect, that the action of the reference background is not able to capture everything about what's happening in the target background. So you know that, so you will know that that something's wrong with the formal computations I've been doing. So in a few cases, one can actually check these things explicitly. So one case is if you choose this defect operator to be zero. Okay. So if you choose the defect operator to be zero, you find that, okay, in my computation of the action of the background independence, you get the action of the target background plus some other terms which formally vanish on shell, okay? But those terms which vanish on shell involve an operator which would imply the triviality of the S matrix around the perturbative vacuum. So you know that in that context where the defect operator vanishes identically, okay, you know in that context that I'm able to see in a fairly clear way that the computations that I'm doing are not allowed or not physically meaningful. So okay. I don't know if that clarifies it.
The first question I asked, you actually didn't answer. So do you need some conformal properties of the defect?
No, not a priori. The only condition is that, well, this non-degeneracy condition is the condition. And you know, for example, that means that they cannot be factorizing defects. Okay. So they could be topological defects. That might be really nice, but I think those, I don't know how general you can expect this construction to be if you restrict attention to such kinds of defects.
Okay. Okay, thank you.
Ashok?
Yeah, so I have, I think, a follow-up on this, that suppose the non-degeneracy condition fails, and you cannot go from A to B. Is it possible that you can go from A to C and then come back to B?
I don't know, maybe. But that would, well, I would guess that wouldn't be possible if a condition like this gives a consistent picture of the string backgrounds.
So that presumably should follow from some relation between these products, right? That maybe the condition between A and C is the product of the condition between A and B and C, something like this.
Yeah, so, okay, so if you have a defect, okay, so which goes from A to C, okay, but you want to construct it as a defect that goes from, A to B and then from B to C. And I don't know which one you said was degenerate, right?
Yeah, say from A to C is degenerate so that you cannot do it.
Yes.
But is it possible that you can go from A to B and then from B to C?
Yes. So, okay, so I would guess I haven't thought about this, but I guess my intuition would be, like that of, well, yes, okay, but one has to be distinguished between, so it might be possible that that somehow the composition of these defect operators might be a singular defect operator, but there's some other defect operator which is non-singular. So the question is, if you can find, is it possible that you can go between one background and another? Okay. So I would say that if this is a consistent picture, the answer would be no, that somehow, otherwise this kind of condition would not be sensible.
I see.
So, but actually yeah, so I don't know if such a thing can be proven. But if it could be proven, that might be some evidence in favor of the conjecture. But right now I have no evidence, basically, except for the fact that it kind of arises from trying to think of the closed string background independence as analogous to open string background independence.
Okay, yeah.
Okay, I'm sorry.
Oh, fine, I'm done. Thank you.
Okay, so are there any other more questions? So if not, let's thank Ted again and to all the speakers of today. And we move now to the discussion. So Harold, please.
Thanks a lot, Mikhail, for chairing this second session. So yeah, thanks also to all the speakers of the session. So I suggest we take like 2 minutes break just to take our breath, and then we can come back for the discussion. So yes, thanks. See you in 2 minutes. Yes, Yuji.
Okay. Hi. I have 2 questions to Rajesh.
Hello.
Hello, Rajesh.
Yeah.
Very nice talk. And then in your operational definition of a derivation of the duality, you wrote scattering amplitudes on the string theory side. So my understanding is that so I assume that your vertex operators are satisfy on-shell conditions. right?
Yes.
In the case of ADS, close-string have to go all the way to the boundary. So you have to be something like on-shell state. So
Yes.
Usually the quantity described by the written diagram is something like scattering, on-shell scattering amplitude. Is that right? Is that correct interpretation?
Yes, yeah. So it is the analog of flat space scattering amplitude, but in this case, it reproduces the correlators of the Yang-Mills theory of the boundary theory. But yeah, it is the analog of the flat space, but they are on-shell vertex operators, and you compute them as you would in flat space.
Okay, so this is great. And in the case of the correlation function of the gauge invariant operators can be given by the low energy limit of the gauge invariant operators of open string field theory.
Yes, in principle.
And then in principle.
Yeah.
And then in the case of open bosonic string field theory, the gauge invariant operators can be actually constructed by the on-shell close-string states. So if we consider the Feynman diagrams of the correlation function of the gauge invariant operators in open string field theory, and if we assume that all the holes are closed up, and then it actually takes the form of the on-shell scattering amplitude of closed strings. So do you think it's okay so far?
So I am not sure I completely understood. You're saying if you take the on-shell, if you take the open string field theory diagrams, which compute the gauge invariant correlators, then in some way, so you say, yes, in principle, it should be true that when the holes close up, they should give rise to the closed string on-shell amplitudes. That is indeed, I think, how the open closed string duality should go. Yes. Is that what you were saying? Yeah.
Yeah. If we assume that the theory with all the holes are equivalent to the theory with a back-reacted closed string theory, so I think it is kind of like the derivation under your statement seems to be hold. So then it naturally continue to my second question. So, and in the case of Feynman diagrams of an open string field theory, double line notation is really, it's not just a double line notation, it's really a piece of wordsheet, right?
Absolutely.
So, and then in the case of so you wrote ribbon graphs in the Strebel surface. So do you think you can similarly write the Feynman diagrams of open strings to the Strebel surface form? Do you have any idea?
Yeah, so I should say here that there is a subtlety which people don't really appreciate, I think, very much, which is that normally, to say it in an easy way, normally when we say holes closing up, we replace the holes by the closed string vertex operators. You think of the holes as D-brane boundary states, and you replace them by closed string insertions by sort of integrating over the modulus associated with the boundary, and you say that. But here you're actually, the double line graphs are ones in which the closed strings are inserted at the vertices of the graph. And so it's slightly different from the usual picture one has, in which you think of the holes closing up and getting replaced by closed strings. So in some ways, it's a dual picture, I think. And this is related to the fact, I believe, that if you are looking at Feynman diagrams, that is perturbative in the gauge theory, which is you're expanding around a closed string background, which is highly curved, as opposed to expanding around a flat space closed string background, which gives you your usual D3 branes, and then there's a back reaction, and you sum, but there you have to sum over an infinite number of holes. But when you're doing perturbative quantum field theory, you sum over a finite number of holes, and then you're not really back reacting. Actually, the open string field theory you need to be considering, which I think what the Feynman diagrams give you is really an open string field theory for D-branes in a highly curved ADS background.
That's right.
So, and then you're kind of there, you can, I think of the holes closing up and giving closed strings in that background, but the same highly curved background. So here there's no real back reaction in some sense, because it's really the reorganizing the open strings into closed strings. In some ways, I think this case is simpler than, it's related to what she was saying yesterday also, that you don't have to consider the, in this particular case, I think it should automatically come out even without any kind of a decoupling limit. So there, so as opposed to in the large radius limit. So I'm not sure if I made myself very clear, but I think, yeah, so the open string field theory is really open string field theory of D-branes in a highly curved ADS background. Yes, with that understanding, I think it is correct that the Strebel, the graphs are really giving rise to the open string field theory of that highly curved background. So as opposed to open string field theory of D3 branes and flat space.
I see. So do we need to place D-branes in the highly curved space in the first place? I think that's, I'm a little bit confused because I thought it was an it is an effect of the back reaction.
Yes, that is indeed true when you look at it from the strong coupling end, because there G string n is very large, so the number of holes proliferate, and therefore they back react. But here G string n is very small, so
I see.
Yeah. And you have only a finite, in the free theory, you have only a finite number of holes, which is just the free field Feynman diagrams, the Wick contractions. So there are just a finite number of diagrams.
Yeah. So actually I'm interested in the mapping between the moduli space. So the
okay. Yes.
So then do you think that your dictionary between the ribbon graphs to the Strebel surface may be applicable to the Feynman diagram with the open string with holes and closed string without holes?
That is the idea, that the Strebel parametrization gives you a dictionary from the moduli space of the open strings, namely the Feynman diagrams, to the moduli space of the closed strings, because the Strebel parametrization is giving rise to the closed string moduli space, endpoint functions of the closed string. So the decorated moduli space or whatever, it's giving you the closed string moduli space. So the Feynman graphs are really triangulating that moduli space.
But in the case of open string field theory, it also has a moduli, right?
Yeah, so those moduli are in some sense included when you do a Feynman diagram, because you would do some Schwinger parametrization of the Feynman propagators, and those are included already. So I'm not directly looking at that moduli space and going to the this thing, though I think there is some relation there. But somehow, at least when you consider operators with large number of insertions, that detail seems to go away, and you actually get only a discrete number of points on the closed string moduli space where the Strebel lengths are integers, are proportional to or rational numbers. So these are discrete points in the moduli space. They're not even dense on the moduli. I mean, they are kind of dense in some large n limit, but there are in general there are a finite number of points on the moduli space, so that doesn't seem to know about the open string moduli space. So you get the closed string moduli space as these very discrete special points, which have nothing to do with the open string moduli space.
So in a sense, after integrating over the module.
Yeah, so the integrating over the open string moduli, you get this closed string, you get the support
discrete
on
points.
just a few points, yeah.
So in a sense that the localization mentioned by Bob's talk is a generic property of the free theory limit. Is that what you're saying?
Of the free theory, yes. It is related, I think, to the fact that there are only a finite number of Feynman diagrams, and therefore only a finite number of closed string surfaces really contribute. Of course, as you increase the complexity of the vertex operators, you in principle can access a whole moduli space, because if I consider trace phi to the n, trace many operators with trace phi to the n1, n2, n3, and take n1, n2, n3 very large, then I will sort of densely cover the moduli space. But that's, so in principle, it is there, but I don't see it unless I go to very large operators.
I see. Thank you very much. That's very interesting. Thank you.
Yes, Andrei?
I have a question to Ivo Sachs. You mentioned that you have a situation where a differential does not preserve the product.
Yeah.
It evokes analogy with BV formalism where delta does not preserve the product of functions. Is it different?
It's actually much simpler than that. It's simply because this sort of background BRST operator has a momentum square in it. It's like C times the Hamiltonian, and the Hamiltonian has a P square in it. So it's simply the statement that P squared or the Laplacian doesn't. I mean, it's the Laplacian. Oh, sorry, I was thinking you were thinking about the BV Laplacian. No, it's exactly that statement that the Laplacian doesn't preserve the product of functions. Yeah, precisely.
So you can define then the Haute-Poisson bracket, right? Or
yes, I should. Perhaps that's an idea. Maybe one could indeed do that. Although, yeah, one would have to probably. Yeah, you could try some graded bracket, perhaps, and then try to define a product in this way. The question, to be honest, I didn't try this, but I'm a little skeptical that it would produce what we'd like to get. But it is an interesting idea, and I haven't thought about it.
Okay.
Thank you. That's a good comment, actually. Thanks.
Yes, Yuji.
I also have a question to Ted. Is he there?
He's still in the list.
Ted? Hi, Ted. Okay, maybe I can ask question and somebody else can answer the question. So I was wondering if his construction can apply to supersync field theory. That's my question. So then it doesn't seem to assume any bosonic nature. So, and in the case of an open supersync field theory, existence of the Tachyon vacuum itself seems to be sure. So that's what I wanted to ask, but then Ted is not here. That doesn't seem to be around. It was very interesting, so I wanted to ask more.
Yes, I don't know what I would say, but like from the experience we had in the paper with Martin, Jakub, and Carlos, so like we're also having a very generic formulation in most of the paper, and it was working with both bosonic and superstring. So, so I would say it looks like it should work, but like if one of them wants to comment more.
I can perhaps comment, but I'm not sure it's in Ted's. He might say something else, but I guess what is true is that.
Is back also
Oh,
after,
very good. Then we can.
I mean, you can comment, and then we can hear Ted just after.
I mean, I think it's probably in a way what Ted was saying, but he will probably correct me that, you know, if you can write, if you can connect two solutions by an L infinity morphism, then the L infinity or an L infinity isomorphism, then of course you will go from one L infinity structure to another. But there might be L infinity structure which are not related in this way, but they might nevertheless be there, but they're not related in this way. That's at least what I think, but maybe Ted will correct me.
Is there a question for me? Sorry, I was using restroom.
Actually, I was asking you about my question was your construction can be applied to superstring field theory.
Yes.
In principle.
At least, okay, at least in this kind of homotopy algebraic form. I don't know about the Wessamino-Witten-like form.
But the existence of, so you only need the existence of the tachyon vacuum solution?
Yes.
Right? So then I think in principle you can construct a solution in infinity form as well?
Yes.
So yeah.
There are two comments. One is that this solution in principle, the claim is that if you could find some kind of invertible defect, you could find a classical solution in bosonic string theory describing, you know, type 2A or something, a vacuum of type 2A, if you could find such a defect. Okay, so, but I think there must be some limitations to what this condition must impose some limitations, this non-degeneracy condition. So in that sense, it can work in superstrings, or it could even possibly, okay, that seems too speculative to me, but yeah, so the problem with the superstring is that we don't really have a simple model like Witten's theory with an A infinity structure, where we can really confirm that it's working, okay, at least in a simplified model. So in bosonic string, okay, for open bosonic strings, we can assume that they are some kind of small deformation of the Witten theory. And then I think this picture that I was describing is basically probably the correct picture. For the closed string, for the closed bosonic string, I think it depends whether there's a tachyon vacuum. But if there is, then I would say that it's quite possible that this is the right picture. But it seems, in the context of the closed string, it seems kind of difficult to imagine how we can really get concrete evidence in favor of that it's working, except maybe if this non-degeneracy constraint somehow, you could study that constraint and see if it's physically reasonable. So, okay, one of the questions that I, wondered about was whether, if you have closed string theory and, 9+1 dimensions, is there a vacuum state that has, closed string background with 8+2 dimensions, right? So this you you don't want this to be true, okay, because it would kind of mean that string theory is not physically sensible. So we should have some kind of a criterion for knowing what string backgrounds are really a part of string theory, or at least a part of a string theory that has some space-time interpretation that is relevant to us. So I think this talk that I was giving was somehow kind of, for me, just kind of motivating some proposal.
Hi, Ted. Can I ask a question?
Yes.
Hi. So this tachyon vacuum, I think it's quite puzzling, right? So suppose you are just in type 2 superstring, no d-branes, just empty Minkowski vacuum. So you do closed superstring field theory there. So do you expect to find a closed string tachyon vacuum? And if so, what this state should represent? I mean,
so maybe I was a little imprecise. I think my comment was maybe at type 0 you could. So if you don't have a tachyon, then it becomes much more questionable whether there's a tachyon vacuum. I actually believe that it's possible that there is, but it will be a very non-trivial solution and probably not universal. So the intuition is kind of like if you look at, say, 5-4 theory on a kink, okay, and you look at the kink field theory, okay, so the kink is a topological soliton, and you don't expect to be in that field theory to see the vacua of the potential, and there's no tachyon in that field theory. But nevertheless, okay, at least in that context, you can write down the field redefinition. You can write down the solution explicitly for the vacuum configuration, but it's somehow okay. So it's a very non-trivial configuration, okay, in that kink field theory. So maybe something like that is possible for supersymmetric string theories. But I think there's no real clarity as to how to find it. So you should have tachyon vacuum solutions. Somehow it's really key to this.
I was I was going to ask in the simpler context of the bosonic string itself. We spent with some students here a year trying to find the closed string tachyon vacuum in the level expansion, and there was very little clear evidence that there was one that you could find in the level expansion. So in that case, do you have any ideas of what may be missing, or what would that tachyon vacuum look like?
Well, I think I would ask that question to you. Okay, I just know that you found some tachyon vacuum, I guess maybe decortic order, or somehow, and somehow the expansion and the number of vertices wasn't converging convincingly enough for you, but
that's right. And well, there was a little evidence that maybe the tachyon vacuum would actually kind of be degenerate in the sense of a tachyon potential. The tachyon potential maybe would go down and eventually up again, and somehow the tachyon vacuum was on the far side. That was the best we could think of, but clearly we just don't know how to do that.
Yes. So I would say that, okay, even if I'm not really clear as to the judgment as to why you really don't trust that solution, but I think if that numerical solution is really there, that somehow it started becoming stable when you included higher vertices. I think it's still not clear that it's the tachyon vacuum in the same sense that I require, that is a state without cohomology. So,
yeah, well, you know, the convergence of level expansion for the tachyon vacuum for the open string was so striking good, and in this case, it's very, very complicated, and you have to deal also with the dilaton, which is another massless field, and they roll together, and they.
Yeah, I remember there was some two-dimensional potential.
Yeah, so it just, the numbers jump from one level to another by 30% or something like that, and just very difficult to tell.
Really, was it that bad?
Yeah, no, it was not
the
bad.
energies or the expectation values, or?
Yeah, everything jumped just a little too much, and we only got some idea with the quartic vertex and some hints of the quintic vertex. So I don't know. It's just maybe, you know, the technology has improved enormously. People that do these calculations, level expansion, open strings, can do them very high, and maybe they could do it pretty high for the Bosonic string as well. But it's kind of difficult, and it's sort of. The tachyon potential at every order changes sign, so it just,
yeah.
if you didn't include the dilaton, the cubic tachyon vacuum gets totally destroyed by the quartic interaction of the tachyon itself.
Yeah.
So you have to include the dilaton a little more, and the vacuum sort of comes back, but it has shifted a bit, and so. I don't know. We have all the evidence there, and I suspect that more than brute force will be necessary to make something clear out of this. Maybe, yeah, I don't know. Maybe this tachyon vacuum requires some deformation of the geometry. As you said, maybe it's not so universal, and maybe it includes some other excitations that make it more stable, spatial excitations.
Yeah. So I was thinking of in the context of a supersymmetric system there, but yeah. So, but maybe. So I think you know, for people like Martin and Mathieu, probably the most intimidating part of the closed string tachyon vacuum is not the level expansion, but the vertices, like dealing with solving these quadratic differentials and finding the moduli space and mapping radii.
Right.
I don't know
if you do numerical work, Moller did certainly the quartic vertex and the quintic, and it's all treble differentials, but still it's complicated by the time you try to make an explicit computation. So
is it better with hyperbolic geometry, or?
Well, I think people should first find the open string tachyon vacuum in hyperbolic geometry. I think it's going to be a little non-trivial.
Yes. Okay. Okay.
Barton, can I jump into this discussion?
Please do.
Yeah. So I wonder whether you have ever tried to search for the open string tachyon vacuum in the theory with stubs, because I think you have the large, very large quartic vertex as well, and then it gets destabilized as well. That the level truncation will not work in this context.
Yeah, it probably is true. So no, I never tried adding the stubs and trying to figure out the answer. But if you write the formal homotopy of the string action that implies the redefinition, perhaps at least formally you can write the solution. But in level expansion, I think it would be a very good lesson if we could find, put a little stop in the open string and manage to find still the tachyon vacuum.
So I think this might even be possible analytically if you put somehow wedge state stubs on the Witten vertex. But I never followed through on this thought.
Yeah, actually, we are working on it with my student, Georg.
Yeah, so that might also be a good setting for looking at this homotopy intertwining solution that I was discussing.
I see. Yeah, I apologize. I do not have a camera here, but my internet says my bandwidth is too low. So.
Yeah. So do you have any idea, Martin, how you do the level expansion with open string theory with stubs?
Well, we would have to calculate the vertices. That's the main obstacle, right? For the regular stubs. Of course, we can try to do the wedge stubs, as Ted says, but then we don't need to do anything numerical. We can just do analytic things. Yeah. Barton, now that I see you, I wanted to ask, so have you examined the role of these SU11 singlet conditions or SU11 symmetry in the context of closed string field theory?
Probably not. I think we did this level expansion calculation with Knighton and we used a universal subspace, but no, we didn't explore that.
But have you noticed that the ghost dilaton violates the SU11 singlet condition? Or at least in the minus sector, like the vertex operator is not annihilated by this C del C zero mode of it in the minus sector.
Well, so this ghost dilaton must be included in the level expansion. You cannot throw it out. Is that right?
Well, that's my question. Somehow it goes out of the SU11 singlet subspace.
Well, but we did. So you shouldn't have found 1-point functions of that thing, and I think we did find some 1-point functions of it.
Mm-hmm. Well,
you know, I think, yeah.
I have to double check. So this is your paper with Knighton or some earlier paper?
Paper with Knighton. It's a long paper. There's a long and a short one. It's the long one.
Okay.
Yeah, I think we initially forgot about this field, and then when we went through the analysis, we thought definitely it's coupling, but we didn't consider. I don't think we considered the SU11, and maybe that throws away some fields. But that would be very striking if it throws away that one, because then I think, as we were saying, if you only have the tachyon at this order and there's nothing at the massless level, no other field that you must include at the massless level, then the quartic term in the potential of the tachyon destroys the vacuum. So as you start going a little bit up in level, you lose the tachyon vacuum.
So this was the only reason why you included this term, not to lose the tachyon vacuum?
No, it was not the only reason. I think there was a little theorem that there's some fields that don't need to be included in the effective potential. And at the end of the day, when we reviewed that little theorem, we concluded that you could not get rid of the ghost dilaton.
Mm-hmm.
Is the SU11 a symmetry of the theory? Closed string vortices?
It was a symmetry of the open string vertex.
Yeah, but it's probably not a symmetry of the closed string vertex, right?
Well, so you would have a holomorphic SU11 and an anti-holomorphic SU11, and both would be destroyed.
By what? By?
Yeah, I'm just wondering.
By the twist, maybe, or well, actually, in this closed string field theory, it's a little more serious because you would have to show it's a symmetry of the higher interactions as well.
Yeah, exactly.
Okay, so that's probably what destroys it, if anything.
Mm-hmm.
The higher point functions.
Yeah. But you needed it at the cubic level or at higher point level? The dilaton coupling?
The dilaton coupling, let's see. You know, I think I'll look at the paper. It's people should keep talking in the day. If I remember right, it might be a quartic interaction, or let me see. Here. This discussion should continue. It's the paper is from 2005, and yeah, there's a tachyon coupling to. So there are two terms that matter. There's a cubic term coupling the tachyon to two ghost dilatons, and then a quartic term coupling three tachyons to the ghost dilaton.
Okay. Yeah, so that's probably consistent with what we discussed, right? The cubic term probably has SU11 symmetry because you have two ghost dilatons, right?
Right. Yeah. So you can set it consistently to 0.
Yeah.
Yeah. But the quartic term has a single ghost dilaton. This is equation 1.3 of this paper from 0506077. And the title is Closed String Theory Vacuum with a question mark.
If you want, Barton, you can share your screen also.
Okay. Oh, yeah, that's a possibility. Let's see. Share. So that's the paper. And there's a cubic potential here in the closed string. And the quartic term, and it's so large and negative that there's no critical point. And then
can you zoom or
zoom a little bigger?
Zoom. Yeah, or going full screen or something.
Yeah. And then here is the tachyon dilaton term and the quintic tachyon term. So as I say here, the positive quintic term suffices to compensate, restores the critical points. And, so there's a whole discussion on some technical work, but that was what I suggested. At the end, we came that the only plausible thing was that the tachyon vacuum was far away. Anyway, the universality and the ghost dilaton, and so we have a coupling there. All right, I'll stop sharing.
Oh, thank you, Barton.
Sure. So I think I remember, in fact, Ashok visiting us when we were doing this computation and saying, be aware of the Gauss dilator. And need to include it.
So it's almost the end of the official time. So, Bardon, you want to say more?
No, I think.
I mean, you can if you want. I mean, we have time. It's early here.
No, it's good. I think would be fantastic if this stacking vacuum gets identified. I think it will make an enormous difference for our understanding of the closed string theory. But maybe it's not universal, and that was the problem. I think we've speculated, I think also in some discussions with Ashok, I don't know, maybe Martin is very close to finding this answer, but we thought maybe you need an ADS background or something, and you have to excite the graviton in some way as well.
Can I ask you a related question? Would it be sufficient to neglect all of the massive states?
So in the spirit of universal solutions, you neglect everything except the Gauss dilaton and the mass equals 0. But once you say, oh, well, let's get solutions that maybe depend on the dimensionality of the space, or there's no solution unless it's supported with some gravitational field.
I mean, the reason why I'm asking is, I guess, the usual story that the tachyon is essentially massive. So how can one neglect the higher masses above the graviton and so on, and hope to get something consistent?
But, you know, the thing that we know is that at least in principle, there's nothing about exciting the tachyon and the dilaton makes other fields roll. So tachyon, dilaton, are, of course, are infinitely many massive scalars. But nobody else is forced by a tacpole condition to roll. And at least that's the argument for universality. And but maybe just you don't find any solution unless you allow something else to roll in some way.
Can I ask Barton a question? You also looked at some other solutions in the closed string field theory as well, right? Some conical deficits and...
Yeah, with Yuji, we looked at some, those cones.
Yeah.
So you would say those are really non-perturbative solutions?
Well, I don't know. With Yuji, I think we've managed to find evidence for a solution with the cubic terms and the quadratic terms, and then the quartic was not clear whether it would help or not. Yuji, please, you say something.
Yeah, I don't remember. But in the case of a conical deficit, the existence of the vacuum, the solution is fairly, I think it seems to stay, at least within our analysis. And in the case of superstring, there's an argument for the in the case of superstring, the condensation of the conical tachyon, localized tachyon, can change the deficit angle. That seems to be, I think there are more evidence for this conjecture. by Adams, Polchinski, Silverstein, right?
Yeah, so the question is really whether you really saw it convincingly in closed string field theory. Like, has there been really a success in closed string field theory finding a non-perturbative vacuum state? I interpreted your results as saying yes, but I just wanted to see if you had any thoughts on that.
Well, my recollection was that our analysis was just quadratic and cubic, but there was a nice interplay between the two of them that formed a vacuum that seemed consistent with expectations. I don't remember if we ever had any attempt of showing that this would just be changed little by the higher interactions.
Yes.
I don't know if Eugene remembers.
I think we evaluated the effect of the quadratic potential numerically, and then I don't think we have done much.
This was yeah.
Yeah, I think we evaluated just an effect of the quadratic potential to the how that can modify our solution, right?
Okay. So what year was that, Luigi?
I moved to MIT in 2003.
Yeah.
September 2003. So, and then it did the first collaboration with you and me. So it must be, yeah.
I'll show it here if people want. Just keep showing papers. I'm sorry. Share. The computed tachyon potential find critical points at 70% of the expected change of the deficit angle. Both twisted and untwisted fields help. Yeah, elementary 4-point vertices. Yeah, there was a little bit of elementary 4-point vertices, and I think we did some estimates, maybe. Yeah.
Yeah.
Yeah, again, this thing tends to destabilize it, but then if you include everything else, it stabilizes it again. Okay, so we did some analysis, but I think that analysis should be done more convincingly to prove that things are okay. So anyway, that's it.
Does anyone more questions or want to discuss some topic? It seems that no. So, okay, thanks everyone for this very interesting discussions. So we will meet again tomorrow. So again, there will be a discussion from 7 to 8 a.m. for Boston time, and which will not be recorded and quite informal. And then we start with the talks again at 8 a.m. And in that way, I remind that we have the panel discussion tomorrow. So between Yuji, Ashok, Martin, and Nathan. So, okay. Have a good end of day, evening, and see you tomorrow.
Thanks, Harold. Thanks very much.
Bye-bye. Thanks.
Bye. See you tomorrow.
Bye, everyone.
Bye.
Bye.